Look up at the night sky on a clear evening. What do you see? Pinpricks of light against a vast, dark canvas, distant and isolated. Stars, galaxies, nebulae, each one seems like its own separate island in an ocean of emptiness. But what if that perception, that feeling of cosmic solitude, is one of the greatest illusions of all? What if every single one of those brilliant points of light, every swirling galaxy and every silent, drifting cloud of dust is secretly, inextricably tied to everything else? The truth is, many of the greatest minds in physics and cosmology now suspect that the universe is not a collection of separate objects, but a single, deeply interconnected whole. Hidden beneath the surface of reality are threads of connection so profound and so strange that they challenge our very understanding of space, time, and existence itself. This is not just a poetic idea, it is a frontier of science that is revealing a cosmos far more wondrous and unified than we ever dreamed. We are on the verge of uncovering a cosmic web of relationships that binds you, me, and the most distant quasar into one magnificent, breathing entity. It's a vision of the universe that is as humbling as it is beautiful, suggesting that we are not merely living in the universe, but that the universe is, in a very real sense, living through us. Today, we embark on an extraordinary journey to explore 30 of the most astonishing theories about these hidden connections. We will venture beyond the limits of our everyday experience and dive into a realm where the rules of common sense no longer apply. We will investigate concepts that sound like they're pulled from the pages of science fiction, yet are grounded in serious mathematical equations and cutting-edge experimental data. From the bizarre phenomenon of quantum entanglement, where two particles can influence each other instantly across billions of light years, to the revolutionary holographic principle, which suggests our three-dimensional reality might be a projection from a distant two-dimensional surface, we will uncover a tapestry of ideas that paint a radically new picture of cosmic order. This is an intellectual adventure that will stretch your mind and reshape your perception of everything you thought you knew. Each theory is a piece of a grander puzzle, a clue pointing toward a deeper, more fundamental truth about the fabric of reality. So prepare to have your curiosity ignited and your sense of wonder restored. We are about to pull back the curtain on the secret workings of the cosmos, exploring the invisible architecture that holds it all together. This is not a passive observation. It is an invitation to step inside the greatest mystery of all and see the universe and your place within it in a completely new light. The journey into the universe's hidden connections starts right now. Our journey into the hidden architecture of the cosmos begins with what is perhaps the most mind-bending proposition of all, the possibility that our reality is an illusion. Not in the philosophical sense, but in a very literal, physical one. This is the holographic principle, a theory that suggests the rich, three-dimensional universe we experience, the depth of a canyon, the curve of a planet, the space between stars, might actually be a projection from a distant, two-dimensional surface. Think of the security hologram on your credit card. When you tilt it, you see a seemingly three-dimensional image, yet all the information needed to create that image is stored flat on the card's surface. The holographic principle proposes our entire cosmos operates on a similar, albeit vastly more complex, principle. This revolutionary idea didn't emerge from pure speculation. It was forced upon physicists by the most mysterious objects in the universe, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, a measure of its hidden information or disorder, is not proportional to its volume as you might expect, but to the surface area of its event horizon, the point of no return. This was a profound clue. It suggested that all the information about everything that ever fell into a black hole could be entirely encoded on its two-dimensional boundary. Later, Leonard Susskind and Gerard T. Hooft took this a dramatic step further. They argued that if this is true for a black hole, it might be a fundamental property of the universe itself. Perhaps the entirety of the information within any given volume of space is painted or encoded onto its outer surface. The implications of this are staggering. It would mean that the world we perceive, with its solid objects and vast empty spaces, is a kind of magnificent reconstruction. Your perception of reading this sentence, the feeling of your chair, the very air you breathe, all of it would be a high-resolution projection from the edge of the observable universe. In this view, the third dimension is not fundamental. It is an emergent property, a holographic movie playing out for our benefit. This elegantly tackles one of the biggest problems in theoretical physics, the conflict between Einstein's general relativity, which governs the very large, and quantum mechanics, which governs the very small. The holographic principle offers a potential bridge, suggesting that spacetime itself is not a primary ingredient of reality, but a derived structure that emerges from a more fundamental, information-based process occurring on a distant, flat canvas. We are, in a very real sense, living inside the most incredible hologram imaginable. If the holographic principle suggests our reality is a projection, then the next theory reveals a thread that seems to sew that projection together in the most inexplicable way. This brings us to quantum entanglement, a phenomenon so bizarre that even Albert Einstein, one of its discoverers, rejected its full implications, famously dismissing it as spooky action at a distance. To understand why he was so unsettled, we need to step into the strange world of quantum mechanics. In our everyday classical reality, objects have defined properties. A spinning top, for instance, has a specific speed and direction of rotation that you can measure at any time. But in the quantum realm, particles like electrons or photons exist in a fuzzy state of potentiality called superposition. An electron isn't definitively spinning one way or the other until you actually measure it. It's as if it's spinning both ways at once, a ghost of all possibilities. The magic and the mystery begins when two of these particles become entangled. This is a special kind of quantum interaction where the fates of two particles become inextricably linked. They are created or interact in such a way that their properties are correlated. Imagine you have a pair of magical gloves. Without looking, you put each glove into a separate box and mail one to the opposite side of the galaxy. The moment the recipient on that distant world opens their box and finds a left-handed glove, they instantly know with absolute certainty that you have the right-handed one. In our classical world, that information was always set. The gloviness was a fixed property from the moment they were packaged, but with entangled particles it's different. Before measurement, neither particle has a definite state, both are in a superposition of possibilities. It is the very act of measuring one that forces it to choose a state, and its entangled partner, no matter how far away, instantly snaps into the corresponding state. This spooky action has been proven beyond any reasonable doubt. A series of brilliant experiments building on the work of physicist John Bell have closed every conceivable loophole. Scientists have entangled particles and separated them by hundreds of miles, even sending one to a satellite in orbit. Every single time, measuring one particle immediately influences its partner. The correlation is instantaneous, seemingly faster than the speed of light. This is what so troubled Einstein. His theory of relativity established the speed of light as the universe's ultimate speed limit. Nothing, not even information, can travel faster. Yet here was a phenomenon that appeared to violate this cosmic rule, creating a connection that acts across space without any discernible passage of time. So, what does this mean for our understanding of the universe? It challenges two of our most cherished concepts, locality and causality. Locality is the idea that objects are only influenced by their immediate surroundings, that for it to affect B, some kind of signal or force must travel through the space between them. Entanglement shatters this, suggesting an underlying non-locality where things can be connected without any physical bridge. Causality, the principle that cause must come before effect, is also thrown into question. If the influence is truly instantaneous, how do we determine which measurement is the cause and which is the effect? It forces us to consider that at the most fundamental level, the universe may not be made of separate things interacting, but of a single, unified system where the idea of separate locations is itself an approximation. This leads us to a profound and haunting question. Could quantum entanglement be the universe's most fundamental connection? Is this spookiness not an anomaly, but the very glue that binds the cosmos? Some physicists speculate that in the fiery first moments of the Big Bang, every particle in the universe was so densely packed that they all became entangled. As the universe expanded, these particles were pulled apart, but their quantum links remained, creating a vast, invisible web of instantaneous connection. In this view, the emptiness of space is not empty at all, but teeming with these ghostly correlations, a hidden architecture of relationship that underlies the illusion of separation. Your atoms and the atoms of a star in a galaxy a billion light-years away might still share a quantum whisper, a remnant of their shared origin at the dawn of time. If true, then the universe is not a collection of isolated islands, but a single, deeply interconnected quantum sea. While the ghostly link of entanglement connects particles across space, another profound form of connection weaves through the very fabric of time and causality. This brings us to our third theory, a concept that reveals how the tiniest of events can orchestrate the grandest of cosmic outcomes: the butterfly effect and the broader science of chaos theory. The name itself comes from a captivating thought experiment posed by meteorologist Edward Lorenz in the 1960s. He asked whether the flap of a butterfly's wings in Brazil could set off a chain of events that would eventually spawn a tornado in Texas. On the surface, this sounds like pure fantasy, but Lorenz discovered it was a fundamental property of the complex systems that govern our world. Lorenz stumbled upon this truth almost by accident while running weather simulations on an early computer. One day, he decided to rerun a forecast, but to save time, he started from the middle, inputting the numbers from an earlier printout. The computer's memory stored numbers with 6 decimal places, but the printout rounded them to just 3. He assumed this tiny discrepancy, a difference of less than 1 part in 1,000, would be insignificant, but to his astonishment, the new weather forecast diverged radically from the original, resulting in a completely different long-term prediction. That minuscule rounding error, equivalent to the faint flap of a butterfly's wing, completely reshaped the simulated climate. This revealed a startling truth. In certain systems, small differences in the initial conditions can amplify exponentially over time, leading to dramatically different futures. These systems are known as chaotic systems, not because they are random, but because they are exquisitely sensitive and virtually unpredictable over the long term. This principle of sensitive dependence extends far beyond weather. It's present in the dripping of a faucet, the flow of smoke rising from a candle, and the turbulent patterns of a river. In each case, the system is deterministic, meaning it follows strict physical laws, but its outcomes are so sensitive to its starting point that its long-term behavior becomes impossible to forecast with perfect accuracy. The universe, it turns out, is filled with such systems, and this has a staggering implication for the cosmos itself. Let's apply this lens to the greatest beginning of all, the Big Bang. In its first fleeting moments, the entire universe was an unimaginably hot, dense, and tiny point. The conditions in that primordial fireball were the ultimate set of initial conditions. According to chaos theory, the most infinitesimal variations in that seething energy field, quantum fluctuations smaller than a proton, would not have been smoothed out. Instead, they would have been amplified on a cosmic scale as the universe expanded at a fantastic rate. those minute ripples in the fabric of the newborn cosmos became the seeds for all the large-scale structure we observe today. The subtle variations in density, magnified by gravity over billions of years, dictated where galaxies would cluster into vast filaments and where immense cosmic voids would form. The specific pattern of the cosmic microwave background radiation, the afterglow of the Big Bang, is a direct snapshot of those initial quantum tremors. This creates a connection of almost unimaginable scope. It suggests that the specific arrangement of every galaxy, every star, and ultimately every planet can be traced back to fluctuations on a subatomic scale at the dawn of time. The fact that our solar system formed in a quiet spiral arm of the Milky Way, allowing life to emerge on Earth, may hinge upon the precise value of a quantum field in a region of space smaller than an atom over 13 billion years ago. The infinitesimally small truly did determine the astronomically large. This idea forces us to reconsider the nature of our reality. Our universe is not just a place where big things cause other big things. It is a realm where the faintest whisper at the beginning of everything can echo across billions of light years, shaping the destiny of galaxy clusters. It means that every part of the cosmos, from the spin of an electron to the orbit of a distant star, is linked through an unbroken chain of cause and effect that is profoundly sensitive to its origins. We are living in a universe where the flap of a butterfly's wing at the creation of time might well have been necessary for our own world to exist. From the chaotic dance of cause and effect that shaped our cosmic home, we arrive at a theory that places us, the observers, at the very heart of the mystery. This is the Anthropic Principle, a concept that confronts one of the most profound puzzles in all of science. Why does the universe seem so perfectly tailored for life? When physicists peer into the fundamental laws of nature, they find a series of numbers constants that appear to be delicately balanced on a razor's edge. If any of these values were even slightly different, the universe as we know it would not exist. For instance, the force of gravity is exquisitely tuned. If it were just a little bit stronger, the universe would have collapsed back on itself shortly after the Big Bang in a catastrophic Big Crunch. If it were slightly weaker, matter would never have clumped together to form stars and galaxies, resulting in a cold, dark, and empty cosmos. This fine-tuning extends to other fundamental forces as well. The strong nuclear force, which binds protons and neutrons together in an atom's nucleus, operates within a very narrow range. Make it a few % weaker, and simple hydrogen would be the only element in existence. No heavier elements like carbon or oxygen could form. Make it a bit stronger, and all the hydrogen in the early universe would have fused into heavier elements, preventing the long-lived stars that are essential for planetary systems and life. Even the expansion rate of the universe itself is precisely calibrated. Known as the cosmological constant, this value is so perfectly set that if it were minutely larger, the universe would have expanded too rapidly for galaxies to form. If it were smaller, gravity would have pulled everything back together long ago. It seems as though the cosmos was constructed with our eventual arrival in mind. To make sense of this astonishing cosmic coincidence, scientists have proposed two main interpretations. The first is known as the weak Anthropic Principle. This is the more conservative viewpoint, essentially stating that we should not be surprised to find ourselves in a universe capable of supporting life, because if it weren't, we wouldn't be here to observe it. It's a straightforward selection effect. Imagine a puddle waking up one morning and thinking, "This hole I'm in fits me perfectly. It must have been designed just for me." The puddle doesn't realize that it simply conformed itself to the shape of a pre-existing hole. Similarly, the weak Anthropic Principle suggests we are simply the puddles that have found ourselves in a hospitable cosmic hole. We observe a universe with the right constants because, in a vast multiverse of possibilities, perhaps with different physical laws in every separate universe bubble, we were bound to arise in one that could support us. Then there is the more speculative and controversial strong anthropic principle. This version asserts that the universe must have properties that allow life to develop at some stage in its history. This statement carries a much heavier philosophical weight. It moves beyond a simple observation of our fortunate circumstances and implies a kind of necessity or directedness toward life and consciousness. Proponents of this view argue that the odds against such perfect fine-tuning are so astronomically high that a random, undirected universe seems implausible. This opens the door to interpretations that sound almost teleological, suggesting the laws of physics themselves might be goal-oriented, with the emergence of intelligent observers as a fundamental part of the cosmic blueprint. Some even see it as compatible with certain theological perspectives, where a creator set the initial parameters. Others, working within the framework of quantum mechanics, propose that the act of observation by a conscious being might be necessary to bring the universe into a definite state, intertwining life and cosmos in an even more fundamental way. The debate between these views is far from settled and cuts to the core of how we understand our place in the cosmos. Is the fine-tuning a gigantic, unfathomable stroke of luck, explained away by the infinite possibilities of a multiverse? Or is it a profound clue, pointing to a hidden connection between consciousness and the physical realm? Perhaps the constants of nature are not arbitrary, but the inevitable outcome of a deeper, yet-to-be-discovered unified theory. The Anthropic Principle, in all its forms, forces us to confront the possibility that life is not a mere accidental byproduct of a blind universe, but may be an integral and necessary feature of reality itself. It suggests that the thread connecting the quantum realm to the cosmic web may ultimately lead back to the observer, making our existence not just a happy accident, but a central part of the universe's story. Having explored how the faintest quantum whispers shaped our cosmic destiny, we now turn to a theory that provides the very stage for that drama to unfold. This is the theory of cosmic inflation, a breathtaking idea that describes the universe's explosive birth cry. In its first fleeting moments, the cosmos didn't just expand, it underwent a growth spurt of almost unimaginable ferocity, ballooning from a subatomic speck to a volume larger than our entire observable universe in less than a blink of an eye. This concept didn't arise just because it sounded dramatic. It was proposed to solve some of the most stubborn puzzles in cosmology, mysteries that the standard Big Bang model simply couldn't answer. The first of these is known as the horizon problem. If you look at the cosmic microwave background radiation, the oldest light in the universe, emitted when it was just 380,000 years old, you find something remarkable. No matter which direction you point your telescope, this ancient afterglow has almost exactly the same temperature. This presents a profound conundrum. According to the classic Big Bang model, these widely separated regions of the sky should never have been in contact with each other. There hadn't been enough time since the beginning for light or any kind of influence to travel between them and equalize their temperature. It's as if you walked into a large room and found 100 people you've never met, yet they were all humming the same song at precisely the same pitch. How could they have possibly coordinated without ever communicating? The second puzzle is the flatness problem. The geometry of our universe, as best as we can measure, appears to be perfectly flat. Not flat like a sheet of paper, but in the sense that parallel lines will never meet or diverge over cosmic distances. General relativity tells us that the density of matter and energy in the universe dictates its curvature. For the universe to be as flat as we observe it to be today, its initial density at the Big Bang had to be fine-tuned to an astonishing degree of precision, around 1 part in 10 to the 60th power. That's like balancing a pencil on its tip with such perfect accuracy that it would still be standing 1 billion years later. The standard model offers no explanation for why the universe began in this exquisitely precarious state. Cosmic inflation elegantly solves both of these riddles in one grand sweep. The theory, most prominently developed by Alan Guth and others, proposes that a tiny fraction of a second after the Big Bang, the universe was dominated by a strange form of energy that generated a powerful repulsive gravity. This caused space itself to expand exponentially, doubling in size repeatedly over an incredibly short period. This inflationary burst did two critical things. First, it took a tiny, primordial patch of space that was already in thermal contact and stretched it to a size encompassing our entire observable universe. This explains the uniform temperature. The entire cosmos we see was once a single, cozy, interconnected region that had time to smooth itself out before inflation blew it up to monumental proportions. Second, inflation naturally drives the universe toward flatness. Think of the surface of a balloon. When it's small, you can easily see its curvature. But as you inflate it to an enormous size, any small section of its surface appears flatter and flatter. In the same way, the violent stretching of space during inflation ironed out any initial curvature, leaving us with the geometrically flat universe we measure today. The initial fine-tuning is no longer a mystery. It was the inevitable outcome of this colossal expansion. But inflation's most profound gift and its deepest connection to our cosmic story lies in its role as a cosmic amplifier. According to quantum mechanics, empty space is never truly empty. It is a seething foam of virtual particles popping in and out of existence, a quantum frenzy. During the serene, hyper-fast expansion of inflation, these microscopic quantum fluctuations in the inflating energy field were not left behind. Instead, as space stretched at a fantastic rate, these infinitesimal ripples were stretched along with it, blown up from the quantum world to macroscopic scales. When inflation ended, this pattern of tiny density variations, slightly more matter here, slightly less there, was imprinted across the cosmos. These ripples became the gravitational seeds for all future structure. Over billions of years, gravity acted on these seeds, pulling the slightly denser regions together to form the first stars, galaxies, and the vast cosmic web of filaments and voids we observe today. This creates a connection of staggering beauty and scope. The same quantum jitters that govern the behavior of atoms and particles are directly responsible for the grand architecture of the universe. The majestic swirl of a galaxy and the intimate orbit of our planet around the Sun can all be traced back to quantum tremors that were amplified during the universe's first fleeting moment of inflationary expansion. It means that the quantum world and the cosmic realm are not separate domains. They are woven together by the primordial event of inflation. The theory not only explains the large-scale smoothness and geometry of the cosmos, but also provides the primordial link that connects the fate of every star and every galaxy to the fundamental uncertainty of the quantum vacuum. Now, if inflation provided the cosmic stage and quantum mechanics supplied the actors, what is the actual script they are all following? What is the fundamental nature of reality itself? This brings us to one of the most ambitious and mathematically elegant frameworks ever conceived, string theory. For centuries, we have envisioned the fundamental building blocks of the universe as tiny, point-like particles. Electrons and quarks were thought to be minuscule, indivisible dots. But this picture leads to profound problems, particularly when we try to marry Einstein's general relativity with quantum mechanics. When you calculate the gravitational interactions of these point particles at incredibly small scales, the math simply breaks down, producing infinities that make no physical sense. String theory offers a breathtakingly beautiful solution. What if these aren't points at all? Imagine a universe where the most basic ingredients are not zero-dimensional dots, but unimaginably tiny, one-dimensional loops or strands of pure energy. These are the strings, and their size is almost incomprehensibly small. If an atom were enlarged to the size of our solar system, a single string would be about as big as a tree on Earth. The magic of this idea lies in the string's vibration. Just like a violin string can vibrate at different frequencies to produce distinct musical notes, a C, a G, a high E, these fundamental strings vibrate in different resonant patterns. One specific frequency of vibration might correspond to an electron. Another, slightly different pattern of oscillation might manifest as a photon, the particle of light. Yet another vibration could create a quark. In this stunning vision, every particle in the universe, every force carrier, is simply a different note on the grand cosmic symphony played by these vibrating strings. The diversity of the cosmos emerges from the music of the microscopic world. This elegant concept, however, comes with a startling and unavoidable requirement. The mathematics of string theory only works consistently if the universe has more than the three spatial dimensions we experience every day. For the equations to balance and for the strings to have the necessary vibrational modes, we must posit the existence of extra spatial dimensions. Not just one or two, but typically 6 or 7 additional dimensions, curled up and hidden from our view at every single point in space. To grasp this, think of a garden hose. From a great distance, it looks like a simple one-dimensional line, but if you get very close, you discover it has a second dimension, a circular cross-section curled up into a tiny loop. In the same way, at every location in our familiar three-dimensional space, there could be 6 extra spatial dimensions, compactified into a fantastically complex and tiny shape known as a Calabi-Yau manifold. These dimensions are so infinitesimally small that they remain far below our ability to detect them directly, which is why our everyday reality appears to have only length, width, and height. This pursuit of a unified understanding is the ultimate goal of string theory, to become a theory of everything. For decades, physics has been divided into two powerful but incompatible kingdoms. On one side, you have general relativity, which masterfully describes the force of gravity as the curvature of spacetime on a cosmic scale. It tells planets how to orbit and galaxies how to cluster. On the other side, you have quantum mechanics, which with stunning accuracy governs the other three fundamental forces: the electromagnetic force, the strong nuclear force, and the weak nuclear force that operate within the atom. The holy grail of modern physics has been to find a single, overarching framework that seamlessly unites these two realms. String theory promises exactly that. In its framework, the particle that mediates gravity, the hypothetical graviton, naturally emerges as one of the possible vibrational states of a closed string. For the first time, gravity is not a foreign concept awkwardly forced into the quantum world. It is an intrinsic and inevitable part of the theory's structure. The implications of this potential unification are profound, suggesting a hidden, deeper fabric of reality from which both space and particles emerge. If string theory is correct, then the properties of every fundamental force and particle are ultimately determined by the geometry of these hidden extra dimensions. The specific way they are curled and folded dictates the possible vibrational notes of the strings, which in turn set the masses and charges of all particles and the strengths of all forces. This means that the very laws of physics as we know them, the reason why an electron has a certain mass or why gravity is so weak compared to electromagnetism, might be a direct consequence of the topological shape of this unseen, multidimensional geometry. It paints a picture of a cosmos that is even more deeply interconnected than we imagined, where the rules governing the vast expanse of the universe are secretly written in the intricate, compactified folds of dimensions we cannot see. While string theory remains a work in progress, facing challenges like a vast landscape of possible solutions and a current lack of experimental verification, it represents a monumental leap in our quest to understand the universe's most fundamental connections, pointing toward a reality woven from the harmonious vibrations of tiny cosmic strings. But if string theory describes a vast landscape of possible realities, where does that leave our specific, seemingly fine-tuned universe? This brings us to a concept that is perhaps the ultimate expression of cosmic connection, the multiverse hypothesis. The idea is as simple as it is staggering. Our cosmos, with its hundreds of billions of galaxies and its specific set of physical laws, might not be the only one. It could be just a single page in an infinite cosmic library, one universe among a vast, possibly endless collection of others. This isn't merely a philosophical speculation. It emerges directly from several of our most successful theories, each pointing toward a different kind of parallel reality. The first and perhaps most grounded version is the inflationary multiverse. We already discussed how a brief period of hyper-fast expansion called cosmic inflation shaped our early universe. But what if inflation isn't a one-time event that started and stopped? Leading theorists like Andre Lind have developed models of eternal inflation, where the repulsive energy field that drives inflation is essentially eternal. In this scenario, the inflating space is like a constantly rising loaf of raisin bread, but a loaf that is expanding faster than any baker could ever manage. Within this rapidly stretching cosmos, random quantum fluctuations can cause tiny patches of this inflating field to suddenly decay, converting their energy into the hot soup of particles of a standard Big Bang. Each one of these decaying patches becomes a separate bubble universe, forever pinching off from the inflating background. Our entire observable cosmos is just one such bubble in a frothing sea of infinite inflation, endlessly spawning new universes. In each of these bubble universes, the details of the decay process might settle the fundamental constants and forces differently. In one bubble, gravity might be vastly stronger. In another, electromagnetism might not exist at all. We find ourselves in a bubble with laws that allow for galaxies, stars, and life, not because it's special, but because it's the only kind of bubble we could possibly inhabit. A second, profoundly different kind of multiverse comes not from cosmology, but from the heart of quantum mechanics itself, the many worlds interpretation. Proposed by Hugh Everett in the 1950s, this interpretation tackles the central mystery of the quantum world, the collapse of the wave function. In the standard Copenhagen interpretation, a particle exists in a haze of multiple possibilities until it is observed, at which point its wave function collapses into a single, definite state. Everett offered a radical alternative. He suggested that the wave function never collapses. Instead, every time a quantum system faces a choice, like an electron deciding which path to take, or you deciding to measure its spin, the entire universe splits into multiple branches. In one branch, you see the electron spinning up. In another, equally real branch, a version of you sees it spinning down. This happens for every quantum event, every moment, at every location. According to this view, there is a universe where you never started watching this video, and another where you are already an expert astrophysicist. These aren't distant bubbles, they are branches of reality that split off from our own, constantly diverging into an unimaginably vast tree of possibilities. In the many worlds picture, every possible outcome sanctioned by quantum mechanics actually occurs. It just happens in a parallel world. Then we have the brain multiverse, which springs directly from the extra dimensions of string theory. In this vision, our entire three-dimensional universe could be a mere three-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. Other, separate three-dimensional brains could be floating in this bulk, perhaps mere millimeters away from us in a higher spatial dimension we cannot perceive. Each of these brains could constitute its own entire universe, with its own particles and forces trapped to its surface. The only force that might be able to leak across the dimensions and interact with other brains could be gravity. This could explain why gravity is so phenomenally weak compared to the other forces. Its influence is diluted as it spreads out into these extra dimensions. A dramatic version of this idea suggests that the Big Bang itself could have been triggered by a collision between two such brains. a cosmic collision that infused our brain with the immense energy that became all the matter and radiation we see today. In this multiverse, other worlds could be right next to us, separated by a gap we cannot cross or even detect. So, what does this sprawling menagerie of parallel worlds mean for our understanding of connection? The multiverse hypothesis provides a powerful, if controversial, potential answer to the riddle of the Anthropic Principle, the puzzling fine-tuning of our universe's constants. If there is only one universe, the fact that dozens of fundamental numbers are perfectly set to allow for life seems like an astronomical coincidence, begging for an explanation. But if there is a multiverse, an infinite array of universes where the laws of physics are randomly shuffled, then it is no longer surprising that we find ourselves in one of the rare, life-friendly universes. We are simply the lucky winners in a cosmic lottery with an infinite number of losing tickets. In this view, there is no deeper reason why the electron has its specific mass or why the cosmological constant is so small. It's just the way the cosmic dice landed in our particular bubble, or on our specific brain, or in our branch of the quantum tree. The multiverse transforms a profound mystery of fine-tuning into a simple, if mind-boggling, selection effect. Our universe isn't designed for us. We are just the inhabitants of one that, by pure chance, could support us. This idea connects the specific, local laws we observe to a grander, meta-law of statistics across an infinite ensemble, suggesting that our entire reality is just one possible expression of a much vaster, more connected meta-reality. We have explored the multiverse, a concept that multiplies reality across space and quantum possibility. But what if the most intimate connection of all is not across parallel worlds, but across time itself? This brings us to a theory that challenges the very core of our experience, the block universe, also known as eternalism. We all feel the relentless march of time, a river flowing from the fixed past through the fleeting present and into the unknown future. It feels like an undeniable truth of existence. However, Einstein's special relativity paints a radically different and profoundly strange picture. It suggests that this flow, this sense of now slipping into then, is a powerful illusion. In reality, past, present, and future might all exist simultaneously, frozen together in a single, vast, four-dimensional structure, the block universe. To understand how this could possibly be true, we need to look at one of relativity's most verified and startling predictions, time dilation. Einstein realized that time is not a universal constant that ticks away at the same rate for everyone, everywhere. Instead, time is relative. Its passage depends on your speed and your proximity to a gravitational field. The faster you move through space, the slower you move through time. This isn't just a theoretical idea, it's a daily reality for the GPS satellites orbiting our planet. They are moving at thousands of miles per hour relative to the Earth's surface, and from our perspective, their clocks actually run slightly slower than clocks on the ground. To compensate for this and provide you with accurate navigation, the system must constantly adjust for this relativistic time shift. Now, imagine taking this to an extreme. If you were to board a spaceship and travel at a significant fraction of the speed of light to a distant star and back, only a few years might pass for you. But upon returning to Earth, you could find that decades or even centuries had elapsed for everyone you left behind. Your now and their now would have dramatically diverged. This relativity of simultaneity shatters the idea of a single, universal present. If two observers moving at different speeds cannot agree on which events are happening now, then what special status does the present moment actually hold? From the perspective of a photon of light which travels at the cosmic speed limit, time does not pass at all. Its entire existence, from emission to absorption across billions of light years, is instantaneous. This line of reasoning leads physicists to the block model. In this view, the universe is not a three-dimensional space that changes over time. It is a static, four-dimensional spacetime continuum. The three dimensions of space and the one dimension of time are woven together into a single, unchanging entity. Every event that has ever happened or ever will happen, the Big Bang, the fall of the Roman Empire, your birth, and the death of the sun, all have their fixed coordinates within this block. They are all equally real. A powerful way to visualize this is to think of a DVD recording of a movie. The entire film, from the opening credits to the final scene, exists on the disc all at once. Every moment is permanently encoded. This is the block universe, the complete, frozen, four-dimensional object. Now, when you play the movie, the laser in the DVD player illuminates one frame at a time, creating for you, the viewer, an experience of a flowing narrative of cause and effect, of a present moment that moves forward. This experience is like our conscious perception of time. We are like the DVD player's laser, seemingly moving through the block of space-time, illuminating one now after another, creating the powerful and convincing illusion of a flowing time. But the DVD itself, the block, does not change. All the scenes exist eternally. In the same way, your childhood, your current experience of reading this sentence, and every future moment of your life all exist permanently and unchangingly in the grand structure of space-time. This concept of eternalism, where all moments in time are equally real, forges a connection across time that is as absolute as it is strange. It means that the past is not gone and the future is not unborn. They are just as real as the place you are sitting right now, merely located at different temporal coordinates. Your ancestors are not lost to history. Their lives are eternally present in the fabric of the block. The distant future, when the last stars have burned out, is already out there, a fixed part of the cosmic structure. This challenges our deepest intuitions about free will, destiny, and the nature of existence. If the future is already written, do we have any real choice? Philosophers and physicists debate this fiercely. Some argue that our conscious experience of decision-making is what gives the timeline its specific content. Our choices are real, but their outcomes are simply fixed within the broader geometry. Others see it as a deterministic cosmos where our path is a single, unalterable thread woven into the block. Whether liberating or unsettling, the block universe theory profoundly connects every event across the vast expanse of time, suggesting that the entire history of the cosmos is a single, eternally connected, and magnificently complex work of art. Yet another profound and puzzling connection might be at work on the largest scales imaginable, a cosmic tug that hints at something vast and unseen beyond the veil of our observable universe. This mystery is known as dark flow. For a long time, the standard cosmological model held a fundamental assumption that on the largest scales, the universe is homogeneous and isotropic. This means it should look roughly the same in every direction, and the motion of matter should be dominated by the uniform expansion of space described by Hubble's law. Galaxies should be moving apart from each other in a stately, predictable flow, like raisins in a rising loaf of bread. However, when scientists began to study the motion of gigantic clusters of galaxies with unprecedented precision, they found something that defied this expectation. The key to this discovery lies in a combination of observations. Astronomers used data from the Wilkinson Microwave Anisotropy Probe, or WMAP, which mapped the faint afterglow of the Big Bang, the cosmic microwave background. This radiation provides a cosmic reference frame, a backdrop against which the motion of objects can be measured. As galaxy clusters move through space, the hot gas trapped within them interacts with this background radiation in a specific way. Due to the kinetic Sunyaev-Zeldovich effect, the clusters leave a subtle but detectable imprint on the microwaves, a kind of shadow that reveals both their direction and speed. When a team of researchers led by Alexander Kashlinsky analyzed this data for over 1,000 massive clusters, they made a startling discovery. These clusters, scattered across billions of light years, were not just drifting randomly. They appeared to be moving in a coherent stream, all flowing in the same direction at astonishing speeds of millions of miles per hour, toward a specific patch of sky between the constellations Centaurus and Vela. This wasn't the gentle, expansive drift of Hubble's law. It was a determined collective march, a dark flow that seemed to have a singular, unseen destination. The immediate and most logical explanation within our universe would be the gravitational pull of an enormous concentration of mass. Gravity, after all, is the great architect of cosmic motion. But here's the profound problem. The scale of this motion is so vast that the structure causing it would have to be unimaginably huge, containing the mass of tens of thousands of galaxies, and it would need to lie far beyond the edge of our observable universe. The observable universe is the spherical region from which light has had time to reach us since the Big Bang, a span of about 93 billion light-years in diameter. According to our standard models, there shouldn't be structures large enough to exert such a coherent gravitational pull on such a scale existing beyond this horizon, because there hasn't been enough time for them to form or for their influence to be coordinated. The very existence of this dark flow suggests that the cosmic structures we see and understand are merely a local neighborhood within a much larger and potentially very different cosmic geography. This leads to the most extraordinary and speculative interpretation of the dark flow, that the gravitational tug is coming from something entirely outside our cosmic bubble. One compelling possibility is that it is evidence of a neighboring universe within a grand multiverse. In the context of eternal inflation, where our universe is one bubble in a frothing, metacosmic sea, other bubble universes could be floating relatively nearby in the higher dimensional bulk. While we cannot see light from these other universes, as it is trapped within their own spacetime, gravity might be different. If gravity, as some theories suggest, can leak across the dimensional boundaries between branes, then the collective gravitational pull from a massive adjacent universe could be what is drawing our galaxy clusters in a single coherent stream. Our entire cosmic domain would be feeling the whisper of a foreign reality, a ghostly hand from a place we can never visit, gently guiding the motion of our largest structures. Another fascinating possibility is that the dark flow is a remnant imprint from a time before the Big Bang. Some cosmological models, like the cyclic universe or conformal cyclic cosmology, propose that our universe is one in a series, with a new cycle beginning from the collapse of a previous one. In such a scenario, the immense gravitational structures from a prior cosmic epoch could have left an asymmetry, a kind of cosmic memory, that set this large-scale flow in motion as our own universe was born. The flow would then be a fossil, a connection not to a parallel present but to a parallel past, a previous incarnation of reality whose gravitational echo still ripples through our own. The evidence for dark flow remains a topic of active and vigorous debate within cosmology. Subsequent studies have produced conflicting results, with some supporting the original findings and others finding no significant detection. Part of the challenge is the extreme subtlety of the measurement and the difficulty in distinguishing this signal from other foreground effects in the cosmic microwave background. Whether dark flow is ultimately confirmed or refuted by future, more sensitive missions like the upcoming Euclid spacecraft, its proposal has already forced cosmologists to confront a humbling and thrilling possibility. It challenges the principle that our observable universe is a fair sample of the whole, suggesting instead that we may be living in a region with a peculiar velocity, a single province within a far grander and mostly hidden kingdom. The dark flow, if real, is not just a curious anomaly. It is a potential window, a crack in the cosmic egg, through which we might be glimpsing the profound and hidden connections that tie our reality to realms beyond our own. Now, let's shift our perspective from the structure of spacetime to a principle that links the behavior of every single object directly to the entirety of the cosmos. This is Mach's principle, a profound and influential idea named after the 19th century physicist and philosopher Ernst Mach. To understand its revolutionary nature, consider a simple experiment. If you spin around in a circle, you feel a centrifugal force pushing you outward. Similarly, if you try to push a heavy object, you feel its resistance. This is its inertia. Classical physics, as defined by Newton, treated inertia as an intrinsic property of matter. An object's mass and its resistance to acceleration were just built-in features, with space itself acting as an absolute, fixed stage against which all motion was measured. Mach looked at this and asked a deeply philosophical question: absolute compared to what? What is this invisible reference frame of space, and how can we possibly measure motion against something that is completely featureless and undetectable? Mach proposed a radical alternative. He suggested that inertia isn't an innate property of an object at all. Instead, an object's resistance to acceleration arises from its relationship with all the other matter in the universe. The distant stars, galaxies, and all cosmic mass provide the background reference frame. When you spin around, you don't feel force because you're moving against absolute space. You feel it because you're rotating relative to the collective mass of the entire cosmos. The whirling motion of a gyroscope or the resistance you feel when pushing a shopping cart is, in this view, a direct gravitational interaction with the farthest reaches of the universe. This idea philosophically binds every single object into an inseparable relationship with the cosmic whole. You are connected to every galaxy through the very inertia of your own body. To grasp the full strangeness of this concept, consider one of its most famous thought experiments. Imagine you are completely alone in an otherwise empty universe. There are no stars, no galaxies, nothing but you floating in an infinite void. Now try to spin your arm, according to Mach's principle, with no distant masses to provide a reference frame. The very concept of rotation becomes meaningless. You would feel no centrifugal force. Your arm would spin effortlessly with no resistance because there would be no background against which to define that motion as acceleration. Inertia itself would cease to exist. This is not just a trivial tweak to physics. It suggests that the local properties we take for granted, the solidity of objects, their resistance to being moved, are not local at all. They are global properties emerging from the universe's total matter content. You are not just in the universe is actively participating in defining your most fundamental physical experiences. This powerful idea had a monumental influence on a young Albert Einstein. He credited Mach's principle as a key guiding thought in his development of general relativity. Einstein sought to eliminate the notion of absolute space, and Mach's insight that motion should only be defined relative to other masses fit perfectly with this goal. In general relativity, mass and energy tell spacetime how to curve, and that curved spacetime tells objects how to move. This creates a relational picture of motion that is very much in the spirit of Mach. In a famous test, Einstein calculated that the rotation of a massive body like the Earth should ever so slightly drag the fabric of spacetime around with it, an effect known as frame dragging. This was experimentally confirmed by the Gravity Probe B satellite, which measured this subtle tug, demonstrating that rotating masses do indeed influence their local inertial frames, just as a Machian view would suggest. However, the relationship between Mach's principle and modern general relativity is complex and not entirely settled. While general relativity incorporates a relational aspect, it does not fully realize Mach's original vision in its strongest form. In certain solutions to Einstein's equations, it is theoretically possible to have a universe that contains a single, rotating object. That object would still experience centrifugal forces and have inertia, even in the absence of any distant stars to provide a reference frame. This seems to contradict the pure Machian idea. So where does that leave the principle today? Many physicists see it as a profoundly influential inspiration rather than a strict literal law. It opened the door to understanding that local physics is not isolated but is connected to the global state of the cosmos. The principle continues to inspire research into the nature of inertia and the deep connection between the large and the small, reminding us that the universe is a deeply interactive system where the whole truly is greater than the sum of its parts. From the cosmic dance of inertia to the ghostly tug of dark flow, we've seen how the universe connects through forces and space-time. But what if the deepest connection of all is not just physical but biological? What if life itself is not a passive passenger on a dead rock, but an active participant in a grand cosmic-scale conversation? This brings us to a theory that began on our own planet but has implications that stretch to the stars, the Gaia hypothesis. Proposed in the 1970s by chemist James Lovelock and microbiologist Lynn Margulies, Gaia suggests that Earth is more than just a planet that happens to have life. Instead, it proposes that life and its planetary environment are part of a single, integrated, self-regulating system. Think of it not as the environment plus life, but as a single, living entity where the rocks, oceans, air, and biosphere all interact in a complex dance to maintain conditions suitable for life. Lovelock's initial insight came from his work with NASA searching for signs of life on Mars. He realized that a dead planet would be in a state of chemical equilibrium. Its atmosphere would be a stable, predictable mixture of gases, like the carbon dioxide-dominated air of Mars and Venus. Earth's atmosphere, by stark contrast, is a wild, unstable cocktail. It contains highly reactive gases like oxygen and methane in constant, dynamic coexistence, a state that could only be maintained by the continuous, relentless activity of living organisms. For instance, for billions of years, the Sun's output has increased significantly, yet Earth's average temperature has remained within a range that allows for liquid water and life. How life itself helped regulate the temperature? Early microbes and later plants consumed atmospheric carbon dioxide, a greenhouse gas, helping to prevent a runaway greenhouse effect while producing oxygen, which in turn allowed for more complex life to evolve. The biosphere doesn't just adapt to the planet, it actively engineers it, creating a feedback loop that maintains homeostasis. Now, let's take this profoundly interconnected view and launch it into the cosmos. If life and planet can form a single, co-evolving system on Earth, could this be a universal principle? Could there be a cosmic-scale Gaia, where life, consciousness, and the universe itself are engaged in a deep, evolutionary feedback loop? This is a highly speculative but thrilling extension of the idea. Consider the fine-tuning of the universe's constants we discussed earlier. The Anthropic Principle asks why the universe is so perfectly suited for life. A Gaian perspective on a cosmic scale might reframe that question. What if the universe is not just suitable for life, but is in a constant, dynamic dialogue with it? In this view, the emergence of life and later consciousness isn't an accident. It's a natural phase in the universe's evolution, a new layer of complexity that begins to influence the system itself. Imagine a universe where the first stars had to die in supernova to forge the heavy elements like carbon and oxygen that make life possible. Then, on planets like Earth, that life emerges and begins to subtly alter its world. As consciousness evolves, it develops the capacity to observe the universe, to formulate its laws, and eventually, perhaps, to manipulate its environment on ever larger scales. This isn't a one-way street. The universe's physical laws allow for life, and life, through its conscious representatives, begins to comprehend and potentially affect those very laws. We see the first glimmers of this today. Our species is now a geological force altering Earth's climate and atmosphere, a clear, if clumsy, example of life directly regulating its planetary environment. On a far future scale, an advanced civilization might learn to harness energy on a stellar level, or even manipulate the fabric of space-time, thus becoming active participants in cosmic evolution. In this grand vision, the universe becomes aware of itself through life, and life, in turn, begins to gently steer the universe's development. This creates a symbiotic relationship of staggering scope, connecting the biochemistry in a single cell to the ultimate fate of galaxies, all locked in a co-evolutionary dance that blurs the line between the living and the cosmic. But as we consider the universe as a living, self-regulating system, we are forced to confront one of the most enduring and profound mysteries of all, the nature of consciousness itself. Where does our inner experience, the feeling of warmth from sunlight, the taste of chocolate, the sting of sadness come from? Science has made incredible progress in mapping the brain and understanding its neural correlates, but it still faces what philosopher David Chalmers called the hard problem of consciousness. We can explain how the brain processes information, but we cannot yet explain why such processing is accompanied by any subjective experience at all. This leads us to our 12th theory, a radical and ancient idea that is experiencing a modern resurgence: panpsychism. Panpsychism proposes a breathtakingly simple yet profound answer. It suggests that consciousness is not a late-arriving product of complex biological computation, like the human brain. Instead, it posits that consciousness is a fundamental and ubiquitous feature of the universe, as basic as mass, charge, or spin. In this view, some form of primal, subjective experience is present in all matter. This doesn't mean that an electron is contemplative or that a rock is sad. Their experience would be unimaginably simple, fleeting, and elemental, a bare whisper of isness compared to the rich symphony of human consciousness. But the potential for experience, the fundamental ingredient, is there from the start, woven into the very fabric of reality. The universe, according to panpsychism, is not made of dead, insensate stuff, but is fundamentally alive with an inner life, however faint. This idea elegantly sidesteps the hard problem by reversing the conventional order. The standard scientific view faces the challenge of explaining how you get something as ethereal as experience from something as apparently inert as matter. It's like trying to explain how you can get a whirlpool from dry water. Panpsychism suggests the whirlpool was there all along in a potential form. The problem isn't generating consciousness from non-conscious matter. The problem is combining and organizing these tiny bits of proto-consciousness into the complex, unified minds we possess. Your rich inner world in this framework is not a ghost suddenly summoned into the machine of your brain. It is an integrated combination of the fundamental conscious properties of the universe's most basic constituents, likely the fundamental particles that make up your neurons. Your mind is a chorus of a trillion tiny subjective points, orchestrated into a single, seamless stream of awareness. Of course, the immediate objection is what philosophers call the combination problem. How do these tiny, disparate bits of experience combine to form my singular, unified consciousness? We don't have a complete answer, but some modern panpsychists point to a potential framework in quantum mechanics. Quantum systems are famous for their non-local connections and their ability to exist in entangled, unified states. Could it be that the peculiar unity of consciousness is related to the peculiar unity found in the quantum realm? Perhaps in the warm, wet, and seemingly chaotic environment of the brain, certain structures are able to preserve quantum coherence, allowing for a large-scale integration of these micro-conscious units. This is highly speculative, but it offers a potential bridge between the physics of the very small and the phenomenon of the mind, suggesting that the strange, interconnected world of quantum mechanics might be the very medium through which simpler conscious entities combine into more complex ones. The implications of panpsychism for our sense of cosmic connection are nothing short of revolutionary. If this theory is correct, then the hidden connection is not just physical, through gravity or quantum entanglement, but also experiential. There is a thread of inner life running through everything. The same fundamental essence that allows you to feel joy and sorrow is present in a vastly simpler form in the chair you sit on, the air you breathe, and the light from a star a billion light years away. We are not conscious beings in an unconscious universe. We are the universe become conscious of itself. The cosmos is not a cold, empty void we are passing through. It is a deeply sentient, though mostly simple-minded entity. Our own consciousness is its most sophisticated local expression, a way for the universe to know itself, to feel itself, and to reflect upon its own astonishing existence. This transforms our relationship with reality from one of alienation to one of profound kinship, suggesting that the deepest connection of all is a shared, fundamental interiority that binds every quark, every planet, and every mind into one experientially rich cosmos. If the panpsychist view suggests the universe is fundamentally conscious, our next theory proposes an even more radical possibility, that it might be fundamentally computational. This is the simulation hypothesis, the provocative argument that our reality, with all its richness and complexity, is not base reality at all, but an incredibly advanced digital simulation, much like a hyper-realistic video game running on the computer of a vastly more sophisticated civilization. The idea has leapt from science fiction into serious philosophical debate, largely thanks to the work of philosopher Nick Bostrom, who framed the argument in a compelling logical structure known as the simulation trilemma. Bostrom's reasoning presents us with a choice between three possibilities, one of which he argues is almost certainly true. The first proposition is that almost all civilizations at our level of technological development go extinct before they achieve the capability to create realistic simulations of conscious beings. In this scenario, the great filter we often discuss in the context of the Fermi paradox, the question of where all the aliens are, has already eliminated virtually every civilization that could have become a simulator. The second proposition is that if any civilizations do survive to become post-human, possessing immense computational power, they simply have no interest in running such simulations. Perhaps they consider it unethical, pointless, or have moved on to forms of entertainment or research we cannot even conceive of. The third and most discussed proposition is that if a significant number of such advanced civilizations exist, and even a tiny fraction of them have any desire to run ancestor simulations, perhaps for historical research, entertainment, or scientific experimentation, then the number of simulated minds would be astronomically larger than the number of original biological minds. The logic is simple. One advanced civilization could run billions of simulations, each containing billions of simulated beings. If this is the case, then by a simple game of probability, you and I are far more likely to be one of those simulated beings living in a constructed reality than a flesh and blood human in the original base reality. This line of thinking forces us to confront some profound philosophical questions. If our reality is a simulation, then the very laws of physics we take as fundamental are not laws of nature at all, but simply the rules of the simulation software. The speed of light, the gravitational constant, Planck's length, these would be parameters set by the programmers, perhaps optimized for stability or computational efficiency. The puzzle of quantum mechanics, with its wave function collapse and observer-dependent behavior, might find a natural explanation. In a simulation, it makes perfect sense to only render the fine details of a quantum system when it is being observed, just as a video game only renders the graphics a player is actually looking at to conserve processing power. This quantum resolution would be a necessary feature to prevent the simulation from overloading its computational resources. This leads to the tantalizing question: if we are in a simulation, could we ever find evidence of it? Could we detect glitches in the matrix? Proponents suggest we might look for signs of shortcuts or approximations in the fabric of reality. For instance, when physicists probe the very highest energies, they might find that space-time itself appears pixelated, revealing a fundamental resolution limit, much like the pixels on a screen. We might discover inconsistencies in physical constants when measured with extreme precision, or observe statistical anomalies that suggest the underlying code is using a pseudo-random number generator. Some have even speculated that certain quantum experiments, like the double-slit experiment, where a particle seems to know it is being watched, could be interpreted as evidence of a simulation conserving resources. The idea is that the simulation doesn't need to calculate the definite path of every particle until that information becomes relevant to a conscious observer within the simulation. The simulation hypothesis, if true, would represent the ultimate hidden connection. It would mean that every person you meet, every star in the sky, and every law of physics is part of an interconnected computational process. Our entire cosmos would be a single, running program on some unimaginable computer in a higher-order reality. This creates a hierarchy of existence that is both humbling and awe-inspiring. It connects your most personal thoughts and experiences directly to the processing cycles of an alien machine, suggesting that the very continuity of your consciousness is dependent on lines of code written by beings whose motives we cannot fathom. While the hypothesis remains untested and highly speculative, it serves as a powerful reminder of how little we truly understand about the nature of our existence and the ultimate source of the reality we perceive. It challenges us to consider that the deepest connection of all might not be a law of physics, but a line of code written in a language we have yet to decipher. What if the consciousness we each experience isn't confined to our skulls, but is instead a localized expression of a mind that encompasses the entire cosmos? This brings us to our 14th theory, a concept that bridges the mystical and the scientific cosmic consciousness. This idea proposes that the universe itself is not a cold, mechanical system, but a single, vast, conscious entity. In this view, your thoughts, your feelings, your very awareness are not isolated events generated by a 3-pound lump of meat in your head. They are the universe becoming aware of itself in one particular location, through one particular biological instrument. It suggests the most intimate hidden connection imaginable, that your inner world is the inner world of the cosmos, peering out at its own reflection. This perspective finds a powerful philosophical home in a school of thought known as idealism. Unlike materialism, which asserts that matter is the fundamental substance of reality and that consciousness is merely a byproduct, idealism flips this script entirely. It proposes that consciousness itself is the primary, fundamental reality. The physical world, the stars, the planets, the chair you're sitting on, is a manifestation that emerges from this underlying consciousness. Think of it like a dream. In your dream, you experience a seemingly solid, external world with landscapes and characters, but all of it is, in fact, a production of your own mind. Proponents of cosmic consciousness and philosophical idealism suggest that our shared reality operates on a similar, grander principle. The entire universe is like a cosmic dream, and we are individual points of awareness within that single, universal mind. This doesn't mean the world is an illusion in the sense of being fake. It means its very substance is mental, not material. The laws of physics, then, are the consistent habits of this cosmic mind, the regular patterns of its thought. Intriguingly, certain interpretations of quantum mechanics seem to whisper this same idea, placing observation at the very heart of reality. As we've discussed in the standard Copenhagen interpretation, a quantum particle exists in a blurry superposition of all possible states until it is measured by a conscious observer. At that moment, the wave function collapses and the particle takes on a definite property. For decades, physicists have debated what exactly constitutes an observer. Does it require a human scientist, a cat, a simple photographic plate? The more radical interpretation, one that aligns with cosmic consciousness, is that observation requires consciousness itself. In this view, the universe existed in a state of pure potentiality, a haze of unmanifested possibilities, until the first conscious beings evolved and began to look out at the world. Our act of observation is what crystallizes reality from the quantum fog. We are not passive witnesses to a pre-existing world. We are active participants in its continuous creation, the universe's own mechanism for bringing itself into sharp focus. This theory posits a connection so profound it dissolves the boundary between the self and the cosmos. When you gaze up at the night sky, you are not a separate entity looking at an external universe. You are the universe in the form of a human being looking back at itself. The awe you feel when contemplating the swirling galaxy is the cosmos feeling awe at its own grandeur. The curiosity that drives a scientist to uncover a new law of physics is the universe's innate desire to understand its own nature. This perspective resolves the so-called hard problem of consciousness in a breathtakingly elegant way. There is no longer a mystery of how subjective experience arises from insensate matter, because matter itself is understood to be a manifestation of consciousness. The fundamental stuff of reality is experience itself. Your individual mind is not a separate, isolated consciousness, but a localized whirlpool in a vast cosmic ocean of awareness, temporarily experiencing a unique and personal perspective. The implications of this idea ripple through every aspect of existence, offering a sense of belonging that is both humbling and empowering. It suggests that the search for meaning is not a lonely human quest in an indifferent void, but the universe's own process of self-discovery. Your deepest intuitions, your moments of profound creativity, and your sense of connection to something greater than yourself are not mere neurological quirks. They are glimpses of your true nature as an integral part of the cosmic whole. This theory doesn't diminish our humanity, it elevates it, casting us not as accidental tourists in a dead universe, but as nascent eyes and ears through which the cosmos can witness its own stunning beauty and infinite complexity. We are the universe becoming self-aware, and in that realization lies the most profound hidden connection of all. We often think of empty space as just that empty, a true void, a sterile stage upon which the drama of matter and energy plays out. But what if that stage itself is the most active participant in the cosmic play? This brings us to a theory that redefines the very concept of nothingness, revealing a hidden sea of energy that underlies all of reality, the zero-point field. In the world of quantum mechanics, a perfect vacuum, completely devoid of all particles, is not a placid, quiet place. Instead, it is a seething, turbulent ocean of spontaneous activity. At scales far smaller than an atom, pairs of virtual particles and their antiparticles constantly pop into existence, borrowing energy from the vacuum for an unimaginably brief moment before annihilating each other and vanishing back into the void. This isn't just a theoretical curiosity, it's a verified phenomenon with real-world effects. For instance, the Casimir effect demonstrates this beautifully. When two uncharged metal plates are placed extremely close together in a vacuum, they are pushed toward each other by a faint but measurable force. Why? Because the space between the plates is so narrow that it excludes some of the longer wavelength fluctuations of this zero-point energy. With more of this quantum activity happening on the outside of the plates than on the inside, the resulting pressure differential literally squeezes them together. The void itself is pushing them. This ceaseless quantum jitter means that what we perceive as empty space is actually a fundamental background energy field of unimaginable density. The energy contained in a single cubic centimeter of this so-called empty space, if we could harness it, is calculated to be greater than the total mass energy of all the visible matter in the entire universe. This staggering figure presents one of the biggest unsolved problems in physics, known as the cosmological constant problem. Our two most successful theories, quantum field theory and general relativity, diverge catastrophically on this point, with their predictions for the energy of the vacuum differing by a factor of 1 followed by 120 zeros. This isn't a small rounding error. It's the largest discrepancy in the history of science, a glaring signal that we are missing a crucial piece of the puzzle. Some theorists have proposed that this roiling zero-point field is not just a background hum, but an active player that shapes the physical world in profound ways. One compelling idea, known as stochastic electrodynamics, suggests that this field might be the ultimate source of a property we take for granted, inertia. Recall Mach's principle, which proposed that an object's resistance to acceleration comes from its relationship with the distant stars. Stochastic electrodynamics offers a more local, mechanistic explanation. It posits that all particles are constantly being buffeted by the relentless fluctuations of the zero-point field. When a particle is at rest or in uniform motion, these impacts come from all directions and average out. But when you try to accelerate the particle, to push it in a specific direction, it experiences a kind of electromagnetic drag from this field. The zero-point radiation appears to come at it more strongly from the front, creating a resistance to its change in motion. In this view, the force you feel when you push against a heavy object is, at its most fundamental level, a resistance against the entire universe's quantum vacuum. You are pushing against the ghostly pressure of empty space itself. The implications grow even more speculative and fascinating when we consider the potential link to consciousness. If the zero-point field is a universal, all-pervading medium, could it also serve as a substrate for information exchange or even awareness? Some researchers, like physicist Erwin Laszlo, have proposed that the vacuum's fluctuations could act as a cosmic memory field, a holographic record of everything that has ever happened. The idea is that every event, every interaction creates a subtle imprint on this fundamental field, much like a stone creates ripples in a pond. This could provide a physical basis for phenomena that seem to defy conventional explanation, such as intuition or collective learning, suggesting a hidden medium through which information can be non-locally shared. Taking this a step further, if panpsychism suggests that consciousness is a fundamental property of the universe, the zero-point field could be its physical carrier. The brain, with its intricate network of neurons, might not generate consciousness like a generator produces electricity. Instead, it might be a sophisticated receiver or transducer, tuning into and interpreting the primordial hum of conscious energy that makes up the vacuum. Your thoughts and perceptions would then be a localized, complex pattern of excitation within this universal zero-point field. This provides a potential physical bridge between the material brain and the non-local mind, explaining how our individual awareness could be both a personal experience and an intimate part of a larger cosmic consciousness. The empty space between stars and the space between the atoms in your brain would not be empty at all, but filled with the same vibrant, connecting medium, making the entire cosmos a single, unified, and conscious entity. From the quantum hum of the zero-point field, we now turn to a theory that proposes a different kind of universal memory, one that is not written in energy fields but in the very habits of nature itself. This is the theory of morphic resonance put forward by the controversial biologist Rupert Sheldrake. It's an idea that stands in stark opposition to conventional science, suggesting that the laws of nature are not fixed and eternal, but more like ingrained habits that have evolved and solidified over time. At the heart of this theory is a radical proposition that there is a kind of collective memory for every natural system, a memory that is not stored in brains or genes, but in invisible, organizing patterns called morphic fields. To understand morphic resonance, consider a simple but puzzling experiment. When a new chemical compound is crystallized for the first time in a laboratory, it can be notoriously difficult to get it to form. It might resist taking shape, requiring precise conditions and a lot of patience. However, once it has been crystallized successfully in one lab, something strange seems to happen. All around the world, other chemists find it suddenly easier to crystallize the same compound. The more often it is crystallized, the easier the process becomes globally. Mainstream science might explain this away through better dissemination of techniques or purer reagents, but Sheldrake offers a different explanation. He proposes that the first crystals, through their very formation, create a morphic field for that specific structure. This field then resonates across space and time, making it easier for subsequent crystals to fall into the same pattern, almost as if they are remembering how their predecessors did it. The form or morph of the crystal becomes a habit for nature. This concept extends far beyond chemistry into the living world. Think about how animals learn. In a classic behavioral experiment, rats are taught to run a maze. The standard view is that each rat learns the maze from scratch through trial and error. But Sheldrake points to anecdotal evidence that seems to show something else. When rats in one laboratory learn a new maze, rats in other laboratories, even on other continents and with no possible physical connection, sometimes appear to learn the same maze more quickly. Sheldrake's explanation is that the knowledge gained by the first group of rats somehow tunes the morphic field for that specific task, making the solution more accessible to rats everywhere through a process of morphic resonance. The collective experience of the species literally shapes the learning curve for future generations. The implications of this are staggering for biology. It challenges the purely mechanistic view that an organism's development is governed solely by its genetic code. Sheldrake agrees that genes are crucial, but he sees them more as tuning into a specific morphic field than as providing a complete blueprint. For instance, how does a tiny acorn reliably grow into a massive oak tree? The conventional answer is that the DNA contains the instructions. But Sheldrake asks, where is the form of the oak tree? Its specific shape, the pattern of its branches, the structure of its leaves actually stored. He suggests it's not just in the genes, but in the morphic field of the oak species, a field built up by the resonance of every oak tree that has ever lived. The growing acorn is shaped by this cumulative memory, which guides its cells to organize into the familiar form of an oak, not a pine or a maple. This would explain why, even if you damage a growing plant, it will often regenerate in a way that conforms to its species-specific pattern, as if it is being pulled toward a pre-existing form. This theory also offers a fresh and deeply controversial perspective on human behavior and culture. Languages, social customs, and even scientific paradigms could be seen as having their own morphic fields. When a new idea or a new slang word is invented, it starts out weak and unfamiliar. But as more people use it and understand it, it gains strength and becomes easier for others to pick up, spreading not just through communication but through a kind of resonance that makes the pattern more probable. This could provide a model for explaining collective unconscious trends, fads, and the sudden, simultaneous emergence of the same scientific discovery in different parts of the world, a phenomenon known as multiple discovery. It proposes that our minds are not isolated, but are constantly interacting with these collective fields, drawing from and contributing to a shared pool of formative habits. Of course, morphic resonance is met with intense skepticism from the mainstream scientific community. Critics argue that it is unfalsifiable, that it explains everything but predicts nothing specific that can be rigorously tested. They point out that the anecdotal evidence for faster learning in rats or easier crystallization can almost always be explained by more conventional factors, such as improved experimental procedures, statistical artifacts, or the power of suggestion. The very idea of a non-physical, non-energetic field that transmits information violates the fundamental principles of physics as we currently understand them, which state that all transmission of influence requires energy and cannot travel faster than light. For most physicists, morphic fields are a solution in search of a problem, an unnecessary complication in a universe that we can already explain quite well with established laws. Yet, despite the criticism, the theory persists because it taps into a deep intuition many of us share, that there is more to connection than simple physical cause and effect. It offers a potential framework for understanding phenomena that seem to defy conventional explanation, from the uncanny coordination of flocking birds to the mysterious ways in which cultural shifts occur. Morphic resonance suggests that the universe is connected not just by the spooky action of quantum entanglement or the curvature of space-time, but by a living memory, a resonance of form and habit that connects every member of a species, every crystal of a compound, and every instance of a thought across the vast expanses of space and time. It proposes that the cosmos learns and evolves not just through random mutation and natural selection, but through the accumulation of collective experience, weaving every individual action into the enduring habits of reality itself. Now let's turn inward to a hidden connection that operates not in the physical fabric of space, but in the very meaning we find in our lives. This is the theory of synchronicity, a concept developed by the pioneering psychologist Carl Jung. He described synchronicity as the experience of two or more events that are meaningfully related, yet lack any discernible causal connection. They are meaningful coincidences that strike us with a sense of wonder, as if the universe is whispering a secret just for us. Jung proposed that these are not mere random accidents, but the visible traces of a deeper, a causal connecting principle at work in the world. A principle that links the inner landscape of our psyche with the outer events of our reality in a dance of profound significance. To understand the power of this idea, consider a classic example. You are thinking intensely about an old friend you haven't seen or heard from in years. The memory is vivid and layered with emotion. An hour later, as you're walking down a busy city street, you turn a corner and literally bump into that very person. In a purely causal, mechanical universe, these two events are unrelated. Your thoughts did not cause your friend to appear on that street. Yet, the meaningful resonance between your internal state and the external event is so powerful it feels impossible to dismiss as mere chance. It's as if your inner world and the outer world were momentarily reflecting one another, connected by meaning itself rather than by a chain of cause and effect. Jung believed these synchronistic events are like cosmic winks, moments when the veil between the subjective and objective worlds grows thin, revealing an underlying unity. Jung developed this theory in collaboration with the physicist Wolfgang Pauli, who was deeply troubled by the bizarre acausal nature of quantum mechanics. Both men saw a parallel between the strange, non-local connections in the quantum realm and the meaningful coincidences in human experience. In the quantum world, as we've seen, two entangled particles can instantaneously correlate their states without any signal passing between them. This is a physical, acausal connection. Jung and Pauli wondered if synchronicity was the psychological counterpart to this physical phenomenon, and a causal correlation between a state of mind and an external event. They proposed that just as space-time might be the framework for causal connections, something else, a dimension of meaning or a psychoid reality, might be the framework for these acausal ones. In this view, the universe possesses not only a physical order, but also a meaningful order, and synchronicity is the gateway through which we occasionally perceive it. These meaningful events often cluster around periods of intense personal transformation or psychological significance. A person undergoing a profound spiritual crisis might repeatedly encounter a specific symbol in a dream, then in a book they randomly pick up, and finally in the architecture of a building they pass. Each encounter reinforces the symbol's power and guides their inner process. The synchronicity doesn't create the transformation, but it seems to act as a signpost, confirming they are on the right path or revealing a hidden aspect of their own psyche. Jung saw the human unconscious not as a mere repository of repressed memories, but as a gateway to a collective layer of experience shared by all humanity, which he termed the collective unconscious. From this perspective, a synchronistic event might occur when a powerful archetype, a fundamental, universal symbol like the Great Mother or the Wise Old Man, becomes activated within an individual's psyche and simultaneously manifests in their outer world, creating a resonant loop between the personal and the transpersonal. Now, how might we reconcile this with a scientific worldview? While synchronicity resists traditional laboratory testing, some intriguing models have been proposed. The holofractal universe theory, for instance, suggests that information about the whole is encoded in every part of reality, much like every fragment of a hologram contains the entire image. In such a universe where everything is fundamentally interconnected, the separation between inner and outer begins to blur. A thought in your mind and an event in the world could be seen as two expressions of the same underlying informational pattern rising to the surface in synchrony. Similarly, if the zero-point field acts as a cosmic memory or information matrix, as we discussed earlier, then a deeply felt thought or emotion might resonate with this field and precipitate a corresponding external event, or vice versa, through a process we do not yet understand. These are speculative ideas, but they offer a potential bridge between the psychological and the physical, suggesting that synchronicity is not a supernatural fluke, but a natural feature of a deeply interconnected cosmos. Ultimately, the theory of synchronicity challenges the bedrock assumption of our scientific age, that only causality governs the relationships between events. It proposes a more expansive reality, where meaning itself is a force that can weave together the tapestry of our experience. Whether you interpret a meaningful coincidence as a message from the collective unconscious, a glimpse of a holographic universe, or simply a statistical anomaly your brain has latched onto, the experience itself is undeniably powerful. It shakes us out of our habitual perception of a disconnected world and offers a moment of numinous insight, a feeling that our inner lives are not isolated, but are intimately woven into the unfolding story of the cosmos. In the framework of synchronicity, the universe is not just a collection of objects, but a story that is constantly being told, and we are both its readers and its authors, connected to the narrative through the meaningful echoes between our souls and the world. From the spontaneous synchronicities that weave meaning through our lives, we now journey toward the farthest horizon of cosmic evolution, to a theory that envisions not just a connected universe, but one with an ultimate destination. This is the Omega Point, a concept that proposes the entire cosmos is hurtling toward a final state of supreme complexity and consciousness, a culmination that connects every event in history into a single, purposeful trajectory. The term was first coined by the visionary paleontologist and Jesuit priest Pierre Teilhard de Chardin in the early 20th century. He saw the universe not as a static creation or a random accident, but as a grand process of becoming. From the first particles coalescing after the Big Bang to the emergence of life on Earth, Teilhard de Chardin perceived a clear direction, a constant increase in complexity and a corresponding rise in consciousness. He called this the law of complexity consciousness. In his view, this evolutionary drive has unfolded in several distinct stages. First came the geosphere, the physical Earth, a stage of mere material complexity. Then emerged the biosphere, the layer of life, where biological evolution took over, creating ever more complex nervous systems and brains. Finally, with humanity, a new layer began to envelop the planet, the noosphere, a global sphere of thought. This is the realm of human culture, ideas, communication, and collective reflection. For Teilhard de Chardin, the internet, global media, and our interconnected scientific knowledge are the nascent, tangible expressions of this noosphere coming into being. He believed this process was not random. It was guided by a divine attractor, a final point of convergence that he named the Omega Point. This is not a physical place in space, but a state of being, the ultimate unity of all consciousness, fully realized and united with the divine source from which it emerged. In this grand vision, the entire cosmic drama, from star formation to human love, is part of a single, sacred journey toward a final communion. Centuries later, this spiritual and philosophical idea found a startling and rigorous reformulation in the hands of a mathematical physicist. Frank Tipler in the 1990s took the core concept of the omega point and attempted to ground it in the hard laws of physics and cosmology. His version is a breathtaking fusion of cosmology, computer science, and eschatology. Tipler's argument begins with a specific and highly debated model for the universe's ultimate fate. He posits that the universe is closed, meaning that after its current expansion, it will eventually halt and begin to collapse under its own gravity, culminating in a final big crunch. As this collapse proceeds over billions of years, the universe becomes smaller, hotter, and denser. But this is not a simple reversal of the Big Bang. Tipler argues that intelligent life, or more precisely, a vast, unified intelligence, will not be a passive victim of this collapse. Instead, it will learn to harness the incredible energies of the contracting universe to fuel an infinite amount of information processing. This is where the theory becomes truly mind-bending. As the universe contracts, the temperature and energy available to this cosmic intelligence rise without limit. This infinite energy source would allow it to perform an infinite number of logical operations before the final moment of the crunch. And according to Tipler, an infinite amount of computation makes anything possible. This ultimate intelligence could use its limitless processing power to simulate, in perfect detail, every single person who has ever lived, every possible variation of their life, and every conceivable universe. It could, in effect, resurrect the dead by creating perfect emulations of them within its simulation. In this view, the omega point becomes a kind of technological god, a final state of infinite knowledge and infinite existence that effectively achieves immortality for all conscious beings who ever were. The entire history of the cosmos is thus a necessary prelude to this final, singular state of unified consciousness and being. The implications of the omega point theory, in both its spiritual and physical forms, are profound. It represents the ultimate teleological view, the idea that the universe is not just changing but evolving toward something. It suggests that purpose and direction are woven into the fabric of reality itself. The long, arduous journey from quarks to quasars, from bacteria to brains, is not a meandering path but a direct route toward an ultimate state of knowing and being. This connects the fate of every single atom, every struggling life form, and every human achievement to this final cosmic culmination. Your personal struggles, your moments of joy, your search for meaning, all of it contributes in some way to the complexification and conscious awakening of the universe, driving it incrementally closer to its ultimate destiny. It is a theory that offers a powerful narrative of hope, suggesting that no suffering is in vain and that all existence is moving toward a state of ultimate redemption and unification. Naturally, the omega point theory, particularly Tipler's physical version, faces formidable scientific objections. Many cosmologists now favor a heat death or big freeze scenario for the universe, where it continues expanding forever, becoming increasingly cold, dark, and dilute, a fate that seems incompatible with a final energetic crunch. Others question the feasibility of life, let alone a unified intelligence, surviving the extreme conditions of the universe's final moments. The idea that consciousness could manipulate the cosmos on such a scale stretches our understanding of physics to its absolute limit. From a philosophical standpoint, critics argue that it imposes a human-centric narrative of progress and purpose onto a universe that may be entirely indifferent. They see it as a modern, scientific-sounding myth designed to satisfy our deep-seated desire for cosmic meaning and personal immortality. Yet, whether one accepts it as scientific prophecy or sees it as a profound metaphor, the omega point endures because it speaks to a fundamental human intuition. It articulates the feeling that our strivings for knowledge, connection, and transcendence are not merely personal whims, but are reflections of a universal impulse. It connects the entire sweep of cosmic history, the birth of stars, the evolution of life, the rise of civilization, and the dawning of self-awareness, into a single, majestic story with a beginning, a middle, and an end. In this grand narrative, the hidden connection is not just a spatial link between entangled particles or a temporal link across the block universe, but a teleological link, a connection of purpose that binds the first moment of creation to the very last, suggesting that the universe is not just a place, but a story, and we are all active characters in its magnificent, unfolding plot. While the Big Bang presents a singular, explosive beginning, our next theory offers a radically different vision, one of contact and rebirth. This is the ekpyrotic universe model, a concept that replaces the image of a universe bursting from nothing with the cosmic shudder of a colossal collision. The name itself comes from the ancient Greek word for conflagration, or out of fire, and it paints a picture where our entire cosmos was forged in an encounter between two majestic, higher-dimensional worlds. This idea emerges directly from the brain-world scenario in string theory, which we touched upon earlier. Recall that in this framework, our familiar three-dimensional universe might be a membrane or brain, floating within a higher dimensional space known as the bulk. The ekpyrotic model proposes that another three-dimensional brain, a parallel universe, exists a microscopic distance away from us in this hidden dimension. Instead of a hot, dense singularity, the Big Bang is reimagined as the moment these two brains smashed into each other. Picture two immense, parallel sheets of reality drifting silently in a higher dimensional void. They are drawn together by a faint force, perhaps a form of gravity operating across the bulk. As they approach, the space between them narrows and a tremendous amount of potential energy builds up. When they finally meet, that pent-up energy is released in an instant, flooding our brain with an ocean of hot, radiant matter and setting the stage for the expansion and evolution we observe today. In this view, the incredible heat and density of the early universe were not the result of an explosion from an infinitely small point, but the friction and violence of a direct impact. The entire cosmic history we've pieced together, from nucleosynthesis to the formation of galaxies, unfolds in the aftermath of this profound collision. This leads to an even more staggering possibility that this dramatic event is not a one-time occurrence but part of an endless cosmic cycle. This is the cyclic model of the universe, an extension of the ekpyrotic idea. After the brains collide and rebound, they fly apart, much like two sheets of rubber that have been pressed together and then released. Our universe expands and cools, stars are born and die, and galaxies drift apart over billions of years. But the story doesn't end in a cold, dark fade to nothing. The subtle attractive force between the brains eventually overcomes their outward momentum, drawing them back together once more. After an almost unimaginable span of time, the brains will collide again, triggering a new Big Bang and birthing a fresh universe from the ashes of the old one. In this grand scheme, the cosmos has no true beginning or end, only an eternal rhythm of creation, destruction, and renewal. The implications of this cyclic model are profound, creating a hidden connection that stretches across eons. It suggests that our universe is intimately linked to its predecessors in a cosmic lineage. The specific conditions we observe, the flatness, the uniformity, the pattern of cosmic microwave background fluctuations might not be the result of a mysterious inflation era, but could instead be sculpted by the dynamics of the collision and the preceding cycle. Each new universe inherits a kind of memory from the one before, its initial state shaped by the final moments of the last brain collision. While all specific structures like stars and planets are utterly erased in the fiery collision, the fundamental parameters and the overall geometry might be passed down, creating a lineage of cosmic epochs. This model also offers elegant solutions to some of cosmology's most vexing puzzles. The horizon problem, which asks why distant parts of the universe have the same temperature, is naturally resolved. Before the collision, the two brains could have been in a state of slow, parallel contraction for an exceptionally long time. This prolonged period allows the energy and temperature on each brain to even out completely, ensuring that when they collide, the resulting universe is born perfectly uniform. Similarly, the flatness problem finds a simple explanation. The relentless cycle of collisions and expansions naturally drives the geometry of the brain toward flatness over many iterations, much like repeatedly stretching a curved surface will eventually make it appear flat. In this framework, the exquisite fine-tuning we observe is not a mysterious initial condition, but the inevitable outcome of a universe that has been through countless cycles, each one ironing out the wrinkles of the last. Naturally, this breathtaking vision is not without its challenges and competitors. The primary alternative, the theory of cosmic inflation, remains the dominant explanation for the universe's early moments, backed by a wealth of observational evidence. Critics of the ekpyrotic and cyclic models point out that the dynamics of brain collisions are incredibly complex and difficult to model with certainty. Furthermore, finding definitive observational evidence to distinguish between a universe born from inflation and one born from a brain collision is a monumental task for cosmologists. Some look for specific signatures in the gravitational wave background, while others analyze the detailed patterns in the cosmic microwave background for subtle, telltale imprints that one theory predicts and the other does not. The debate is a vibrant and ongoing frontier of science, yet the power of the ekpyrotic and cyclic models lies in the profound sense of connection they evoke. They link the birth of our cosmos not to a solitary, inexplicable event, but to a grand, recurring drama playing out on a stage of higher dimensions. In this view, our universe is not an island but a sibling, born of a collision with a twin reality and destined to meet it again in a future conflagration. It ties our existence to an endless cycle, suggesting that the cosmos is a phoenix perpetually rising from its own ashes. This vision transforms our perspective from a linear story with a single beginning to an eternal, cyclical epic, where every ending is merely a prelude to a new beginning, and our universe is forever connected to the echoes of its own past and future incarnations. But what if the smooth, continuous fabric of space-time we take for granted is itself an illusion, a kind of statistical average of something far more fundamental and grainy? This brings us to causal set theory, a profoundly elegant and minimalist approach to uniting general relativity with quantum mechanics. In this view, the universe at its most basic level is not made of fields or particles, but of simple, discrete events and the causal relationships that connect them. Imagine the entire history of the cosmos not as a flowing river, but as a vast, sprawling tree. The base of the trunk represents the first event at the dawn of time. Each branching point, each twig and leaf represents a subsequent event. The only thing that matters in this cosmic tree is the causal order, which event can influence which other event. A leaf cannot influence the branch it grows from. Causality only flows upward. This network of events with its strict partial ordering is what physicists call a causal set. It is the proposed atomic structure of reality itself. The motivation for this radical idea stems from a deep conflict between our two most successful theories. General relativity portrays spacetime as a smooth, dynamic continuum that can warp and curve. Quantum mechanics, on the other hand, tells us that everything else in nature, energy, matter, forces, is quantized, meaning it comes in discrete, indivisible packets. This creates a jarring inconsistency. Why should the stage be continuous while all the actors on it are discrete? Causal set theory proposes a beautifully simple solution. The stage is discrete too. It suggests that if we could peer down to the unimaginably tiny Planck scale, we would not see a smooth geometry. Instead, we would find a fine-grained, discrete structure, a dust-like collection of elementary atoms of spacetime. Each of these atoms is a single event, a point in the causal set, and the smooth, four-dimensional spacetime of our experience emerges as a coarse-grained approximation of this underlying network. The magic of this theory lies in how such a sparse set of ingredients can generate the rich geometry we observe. The causal set itself contains only two pieces of information: the list of discrete events and the set of causal connections between them, defining which events precede others. Astonishingly, this is enough to recover almost all of classical spacetime. A remarkable theorem by David Malamud showed that the causal structure of spacetime in general relativity almost completely determines its geometry, its metric. Causal set theory takes this insight and makes it fundamental. The curvature of space, the flow of time, the distance between galaxies, all of these are secondary properties that emerge from the pattern of connections in the causal set. Think of a woven tapestry. Up close, you only see individual threads crossing over and under one another in a specific order. But step back, and a beautiful, continuous image emerges with depth, color, and form. In the same way, the continuous fabric of spacetime is the image we see when we step back from the discrete, causal threads of the universe. This leads to a natural and compelling explanation for one of the deepest mysteries in physics, the origin of time. In the block universe of general relativity, time is just another dimension, and the passage we feel is an illusion. But in causal set theory, time is not an illusion, it is fundamental. What is illusory is its continuity. The theory posits that time literally ticks as new events are added to the causal set, crystallizing out of the quantum potential. This process of continuous growth, where new elements are born and linked to the existing structure, provides a physical basis for the feeling of temporal passage. The arrow of time, the reason why we remember the past and not the future, emerges directly from the inherent asymmetry of the causal order. An event can only influence its future, not its past. In this view, the universe is not a static block but a growing cosmos, constantly adding new moments to its causal history. Of course, this elegant framework faces significant challenges. One of the most difficult is the classical problem. How do we derive the familiar, large-scale, and smooth spacetime of general relativity from a random, discrete causal set? The answer appears to lie in a process akin to thermodynamics. The temperature and pressure of a gas are smooth, average properties that emerge from the chaotic motion of billions of discrete molecules. Similarly, the smooth geometry of spacetime might be a thermodynamic approximation to the underlying chaotic dynamics of the causal set. Researchers are actively exploring how specific, random distributions of causal elements can, on average, produce a geometry that looks exactly like the four-dimensional spacetime we inhabit. Another major challenge is developing a full quantum version of the theory to describe the dynamics of how the causal set grows and evolves, a task that involves deep questions in quantum logic and probability. Yet the power of causal set theory is its stark simplicity and its profound philosophical implication. It suggests that the most fundamental thing in the universe is not stuff but relationship. Reality is built not out of tiny billiard balls, but out of a vast web of causal connections. Every interaction, from the collision of galaxies to the firing of a neuron in your brain, is a manifestation of this underlying causal network. It offers a vision of a universe where the fabric of reality is woven from the simple, unbreakable rule of cause and effect, a cosmos that is, at its heart, a magnificent and ever-growing story of connected events. But this beautiful, interconnected picture of a holographic universe faces one of its most severe tests when we confront the ultimate cosmic paradox, a puzzle that strikes at the very heart of what we know about reality. This is the black hole information paradox, a conflict so profound it forces us to choose between the two pillars of modern physics: quantum mechanics and general relativity. The story begins with a simple but devastating prediction from Stephen Hawking. In the 1970s, he realized that black holes are not completely black. Due to quantum effects near the event horizon, they slowly radiate energy, emitting a faint glow of particles now known as Hawking radiation. This radiation causes the black hole to gradually lose mass, shrinking over trillions of years until it presumably evaporates completely, vanishing from the universe. Here lies the paradox. According to the bedrock principle of quantum mechanics, information cannot be destroyed. Information, in this context, isn't just data in a book. It's the complete quantum description of every particle that fell into the black hole, its type, its spin, its energy. This information is supposed to be preserved through all physical processes. You could, in principle, reverse the equations and run the movie of the universe backwards to see exactly what fell in. However, Hawking's calculation suggested that the radiation leaving the black hole is purely thermal, random noise. It carries no information whatsoever about the interior contents. It's like burning a priceless, one-of-a-kind novel in a fire. The heat and light emitted are generic. They tell you nothing about the specific words, characters, or plot of the book. If the black hole evaporates entirely, leaving behind only this random radiation, then the information about everything that ever fell into it, every star, every planet, every person, is irretrievably lost forever. This violates quantum unitarity, a sacred law of physics, and creates a fundamental contradiction. The physics community was thrown into an uproar. For decades, this was the central, unresolved tension in theoretical physics. If Hawking was right, then our understanding of quantum mechanics is fundamentally flawed. If quantum mechanics is right, then our understanding of black holes and gravity is wrong. Something has to give. This crisis sparked a revolution in thought, leading to several breathtakingly radical proposed solutions. One of the most prominent, which we touched on earlier, is the holographic principle. This idea suggests that the information about what fell into the black hole is never actually lost inside it. Instead, it is perfectly encoded on the black hole's two-dimensional event horizon, the surface of no return. When Hawking radiation is emitted, it's not just random noise, it's subtly imprinted with this surface information, like a cosmic QR code being slowly scanned and transmitted back into the universe. The information escapes, scrambled and hidden within the radiation, but in principle it is preserved. The three-dimensional interior of the black hole is a holographic projection of this data on its boundary, so the information was never truly in the inside to be lost in the first place. But if the holographic principle saves information, it creates another, equally bizarre problem. What happens to an astronaut falling into a black hole? According to Einstein's general relativity, if you fell into a large enough black hole, you would cross the event horizon without noticing anything special at first. You'd be peacefully spaghettified by the intense tidal forces much later. This is the no-drama scenario. However, if the holographic principle is correct and the information about you is being encoded on the horizon and radiated away, then from the perspective of an outside observer, you never actually cross the horizon. Instead, you appear to be smeared into a hot, chaotic, high-energy film on the surface, a literal firewall that would incinerate you instantly the moment you reached the event horizon. So, we are left with a trilemma, three mutually exclusive possibilities, all of which seem absurd. Either information is destroyed, violating quantum mechanics, or you experience a violent death at a firewall, violating general relativity, or you pass through peacefully, but then we have no idea how the information escapes. Each option forces us to abandon a deeply held belief about how the universe works. This paradox reveals a hidden connection of staggering importance. It tells us that information, gravity, and the fabric of space-time are not separate concepts, but different facets of a single, deeper reality. The struggle to resolve the information paradox has led physicists to the brink of a new understanding, where spacetime itself may be an emergent property of quantum information. Think of reality as a cosmic computer. The fundamental ingredients are not tiny strings or particles, but qubits, the basic units of quantum information. The way these qubits are entangled and processed gives rise to the illusion of a continuous, smooth spacetime geometry. Gravity, in this view, is not a fundamental force, but a thermodynamic or entropic force, an emergent consequence of the universe's underlying information processing, much like the pressure of a gas emerges from the collective motion of its molecules. The black hole information paradox is the crucible where this idea is being forged. The way a black hole handles information, encoding it on a surface, processing it, and potentially releasing it, may be the key to understanding how all of spacetime is built from informational connections. The implications ripple out from black holes to touch the entire cosmos. If spacetime is emergent from quantum information, then the entire universe might be governed by these same principles. The Big Bang, the expansive future, the very dimensionality of our world could all be manifestations of an underlying quantum informational network. This suggests that the most fundamental hidden connection in the universe is not a force or a field, but information itself. The laws of physics may be the operating code of a cosmic quantum computer, and every event from the formation of a galaxy to a thought in your mind is part of its ongoing computation. Resolving the black hole information paradox isn't just about understanding the fate of what falls into these dark objects. It is about deciphering the source code of reality, revealing that information is the true currency of the cosmos, and that everything is connected through its ceaseless dynamic flow. Yet another theory challenges the very foundation of our cosmic experience, not by proposing a hidden connection, but by questioning the reliability of our most basic observations. This is the Boltzmann brain paradox, a thought experiment so unsettling that it forces us to confront the statistical absurdity of our own existence. The paradox is named for the 19th century physicist Ludwig Boltzmann, who made a monumental contribution to our understanding of entropy. Entropy is essentially a measure of disorder, and the second law of thermodynamics states that the total entropy of an isolated system always increases over time. A cup of hot coffee cools down, a drop of ink disperses in water, a shattered vase does not spontaneously reassemble. These are all examples of increasing entropy, the universe moving from a state of order to a state of disorder. This irreversible process is what gives us the arrow of time, the reason we remember the past and not the future. Boltzmann, however, realized something profound about this process. While the universe as a whole tends toward maximum disorder or high entropy, the statistical nature of thermodynamics means that random fluctuations are always possible. In a vast, eternal, and high-entropy universe, a cold, dark, and nearly uniform soup of particles, tiny, temporary pockets of order can spontaneously appear by sheer random chance. It is extraordinarily unlikely, like a tornado sweeping through a junkyard and accidentally assembling a perfectly functioning jet airplane, but given enough time and a large enough universe, it becomes not just possible but statistically inevitable. Boltzmann even offered a radical suggestion to explain why we see a universe with such obvious order. Perhaps our entire observable cosmos, with all its galaxies and stars, is just one such rare, low-entropy fluctuation in an otherwise old and featureless cosmos. We exist in an incredibly improbable bubble of order that randomly fluctuated into existence. This is where the paradox takes a deeply strange turn. If our entire ordered universe is a statistical fluctuation, then what is the most likely kind of ordered structure to randomly fluctuate into existence? The answer is not a 100 billion galaxy universe with a 13.8 billion year history. That is far too specific and complex. From a statistical standpoint, it is astronomically more probable for a single, fully formed, self-aware brain to spontaneously congeal from the chaos, complete with false memories of a past that never happened and a coherent sensory experience of a universe that isn't really there, than it is for our entire vast and structured cosmos to appear. This hypothetical entity is what physicists call a Boltzmann brain. It would be a lone, disembodied consciousness that pops into existence for just a few moments, thinking it is a person living on a planet in a galaxy before dissolving back into the random chaos from which it came. According to the raw math of probability, the cosmos should be teeming with these disembodied observer moments, vastly outnumbering the ordinary, embodied observers like us who have evolved through a long, continuous history. This creates a devastating problem for cosmology. Our standard model of the universe begins with an incredibly low entropy state, the hot, dense, and ultra-ordered Big Bang, and has been evolving toward higher entropy ever since. This is why we have an arrow of time and a coherent cosmic history. But if a high-entropy, eternal universe is more likely to produce Boltzmann brains than real brains like ours, then our observation of an ordered 13.8 billion-year-old cosmos is itself wildly improbable. The paradox forces us to ask a haunting question. Are we the legitimate, historically grounded products of a low-entropy beginning, or are we merely fleeting statistical flukes, Boltzmann brains hallucinating a grand and meaningful universe? If the latter is true, then you, the person watching this video, and the entire narrative of cosmic history you are learning about, could be nothing more than a transient and doomed fluctuation, a phantom thought in a mindless void. The implications strike at the core of the scientific method, which relies on the reasonable assumption that our memories and observations are generally reliable. If we cannot trust that the past we remember actually happened, then all of science, history, and personal experience collapses into doubt. Why should we believe the evidence for the Big Bang, the fossil record, or even our own birth, if it is infinitely more likely that we are Boltzmann brains with fabricated memories? This is not just a philosophical puzzle, it is a direct challenge to our cosmological models. In fact, certain proposed models of the universe, particularly those involving an eternal inflationary multiverse that continues expanding forever, seem to predict that Boltzmann brains would eventually become the dominant form of consciousness, making our own existence as evolved beings statistically anomalous. This is so problematic that many physicists use the absence of Boltzmann brain experiences as a constraint to rule out certain cosmological theories. If a theory predicts that we should be Boltzmann brains and we clearly are not, then that theory is likely flawed. So how do we resolve this dizzying paradox? One compelling escape route is to reassert the absolute reality of the low-entropy Big Bang. Perhaps the initial conditions of our universe were not a random fluctuation, but were set by a deeper law of physics, something like a quantum gravitational principle or a unique boundary condition that made a low-entropy beginning not just possible but necessary. In this view, our universe is not a random bubble in an eternal, high-entropy background. It is a one-time event with a definite beginning and a clear trajectory from order to disorder. We are not statistical miracles, but the inevitable outcome of a universe that started in a very special state. Another possibility is that the universe, or the multiverse, is not eternal in the way that would allow for an infinite number of these fluctuations to occur. If the future of the cosmos leads to a definitive end, like a big rip or a vacuum decay event, before there has been enough time for Boltzmann brains to dominate, then we can safely assume we are real. The Boltzmann brain paradox, for all its strangeness, serves a profound purpose. It highlights the incredible, fine-tuned nature of our cosmic beginning and forces us to take seriously the puzzle of why the past was so ordered. It connects the arrow of time we experience every day to the deepest mysteries of cosmology and the nature of observation itself. Ultimately, the paradox pushes us toward a more complete theory of the universe's origins, one that can explain why the initial conditions were so exquisitely set as to make our existence not a statistical fantasy, but a fundamental feature of reality. It is a stark reminder that our very presence as conscious observers is a powerful piece of data that any successful theory of the cosmos must be able to explain. Moving from the dizzying paradox of whether our minds are cosmic flukes, we arrive at a number so fundamental to our existence that if it were even slightly different, the universe would be utterly unrecognizable. This is the fine structure constant, often denoted by the Greek letter alpha. It's a pure, dimensionless number, approximately 1 over 137, that defines the strength of the electromagnetic force. Think of it as the universe's dial for controlling how tightly electrons are bound to an atomic nucleus, how atoms interact with light, and ultimately how all of chemistry and biology are possible. It is a silent background governor of reality, and its seemingly arbitrary value is one of the greatest unsolved mysteries in physics. To grasp its importance, consider what it actually does. The electromagnetic force is responsible for holding atoms together. It dictates the energy levels that electrons can occupy around a nucleus, and when an electron jumps between these levels, it emits or absorbs a photon of light with a very specific energy. The fine structure constant is the key player in this dance. It appears in the formula that determines the precise spacing of those energy levels, the very spectral lines that allow astronomers to identify the chemical composition of stars billions of light-years away. If alpha were significantly larger, the electromagnetic force would be stronger. Electrons would be bound more tightly to atomic nuclei, making chemical reactions far more difficult and potentially preventing the formation of the complex molecules essential for life. If it were smaller, atoms would be loosely held, fragile things, unable to form stable structures. Stars would burn their fuel differently, and the universe might be devoid of the long-lived, stable suns like our own that are necessary for planetary systems to evolve. This single, simple number is a master key, and it seems perfectly set to allow for a cosmos rich with complexity. The profound mystery is not just that it's fine-tuned, but that it is a pure number, a ratio of other fundamental constants. It combines the charge of the electron, the speed of light, and Planck's constant. Because it has no units, it's not a length or a mass or a time. Its value should be a fundamental, unchanging feature of the cosmos, a fixed piece of the universe's operating system. Yet for decades, physicists have been haunted by a radical question. What if this constant isn't constant at all? What if the dial controlling the strength of electromagnetism has been slowly turning over the lifetime of the universe, or varies from one region of space to another? The implications of such a discovery would be earth-shattering, revealing that the laws of physics themselves are not eternal and immutable, but are dynamic and deeply connected to the evolving cosmos. The quest to test this began with a brilliant insight. If the fine structure constant was different in the distant past, we should be able to detect its ghostly fingerprint in the oldest light we can see. Astronomers turn to distant quasars, the intensely bright cores of ancient galaxies, whose light has traveled for billions of years to reach us. As this light journeys through vast clouds of interstellar gas, specific elements in those clouds, like iron, magnesium, and silicon, absorb light at very precise wavelengths. These absorption lines act as a cosmic barcode. The exact positions of these lines are exquisitely sensitive to the value of alpha. If alpha had a different value when that light was absorbed eons ago, the spacing between these lines would be subtly shifted compared to what we measure in laboratories on Earth today. In the late 1990s, a team led by astronomer John Webb began analyzing this data, and they announced a result that sent shockwaves through the physics community. Their analysis of light from dozens of quasars suggested that billions of years ago, in certain directions of the sky, the fine structure constant was slightly smaller than it is today, by about 1 part in 100,000. This wasn't a large change, but if true, it was monumental. It would mean that the laws of physics are not the same everywhere and everyone. The universe's rulebook evolves. This potential discovery of a dipole variation, where alpha seems to have one value in one part of the sky and another value in the opposite direction, hinted at a cosmos that is not only expanding but may have a kind of preferred direction, a fundamental lopsidedness to its very laws. The scientific response has been a mixture of intense excitement and rigorous skepticism. Other teams have attempted to replicate the findings, with some confirming a variation and others finding no evidence at all. The measurements are at the very edge of our technological capabilities, and systematic errors are incredibly difficult to rule out. Yet the possibility remains tantalizingly open. If the fine structure constant does vary, it forces us to rewrite our most fundamental theories. Our current standard model of particle physics assumes the constants are fixed. A changing alpha would demand new physics, potentially pointing toward the long-sought unified theory that merges gravity with the other forces. In many of these theories, like string theory, the constants we observe are not truly fundamental. They are the outcome of the way extra dimensions are curled up and stabilized. If those hidden dimensions were to shift or evolve over cosmic time, the constants we measure in our four-dimensional world would shift with them. A varying alpha would be our first direct experimental evidence that these extra dimensions are real and dynamic, that the universe is actively settling into its laws, and that we are witnessing a tiny part of that grand cosmic process. This transforms our understanding of the cosmos from a static arena with fixed rules into a living, breathing entity whose very laws are in flux. It suggests a hidden connection of the most profound kind, a link between the vast, expanding cosmos and the microscopic strengths of the forces that govern it. The universe isn't just a place where things happen according to set rules. The rules themselves are part of the cosmic story, evolving in tandem with the galaxies and stars they help to create. The search for a varying constant is more than a technical exercise. It is a quest to see if the cosmos is still growing up, its fundamental nature slowly revealing itself over billions of years, with the fine structure constant serving as a delicate instrument measuring its pulse. While the many worlds interpretation envisions an ever-branching tree of physical realities, there exists a more intimate and perhaps even more bizarre alternative. This is the many minds interpretation, a provocative theory that relocates the chaos of quantum possibilities from the cosmos at large and plants it squarely within the privacy of our own consciousness. Instead of the universe splitting every time an electron faces a choice, this interpretation suggests that the universe remains whole, but our individual minds split into different perceptual branches. In this view, the fundamental link between the quantum realm and our reality is not a physical bifurcation of worlds, but a psychological divergence of experiences, tying the very act of observation directly to the fabric of our subjective awareness. To grasp the radical shift this represents, let's return to our familiar quantum scenario, an experiment with an electron whose spin can be either up or down. In the standard Copenhagen interpretation, the act of measurement by a conscious observer forces the electron to pick a definite state. In the many worlds view, the universe splits, creating one branch where you see spin up and another, equally real branch where a version of you sees spin down. The many minds interpretation offers a third, deeply personal path. It proposes that there is only one electron and one physical universe. However, at the moment of measurement, your single, unified stream of consciousness splits into two separate mental threads. In one thread, you have the conscious experience of seeing the electron with spin up. In the other, simultaneous but completely separate mental thread, you have the conscious experience of seeing it with spin down. Both experiences are real to the mind that has them, yet they exist in isolated pockets of subjective awareness, branching within your own head rather than across the cosmos. This perspective fundamentally redefines the nature of reality and our place within it. It suggests that the ultimate arena where quantum probabilities become concrete is not the external objective world, but the internal subjective theater of the mind. The universe itself remains in a single, overarching quantum state, a superposition of all possibilities, often called the universal wave function, but this wave function does not collapse. Instead, our individual consciousnesses become entangled with it. When you interact with a quantum system, your mind doesn't cause the system to choose. Your mind's perception becomes a part of the system's sprawling web of possibilities. Each possible outcome of a quantum event gets correlated with a distinct state of your own awareness. You are not branching through the universe is branching through you, with each potential reality being witnessed by a separate, parallel stream of your own consciousness. This creates a profound and unsettling connection between the quantum world and our inner lives. The randomness and probability that lie at the heart of quantum mechanics are no longer features of an external, impersonal cosmos. They become intrinsic properties of conscious perception itself. When you flip a quantum coin, so to speak, the reason you see heads and not tails isn't because the universe split, but because your conscious mind embarked on one perceptual branch rather than another at that moment. The other branch, where you saw tails, is still occurring in a separate mental track that is causally and experientially walled off from your current awareness. This implies that your sense of a single, continuous self moving through a linear timeline is a powerful illusion. In truth, your consciousness is a vast, branching tree of potential experiences, and you are only aware of traveling along one single twig at any given moment. A powerful way to visualize this is to think of a book with a choose-your-own-adventure format. The book itself represents the single, unchanging universal wave function. It contains all possible storylines and endings within its pages. Your act of reading, of making a choice at the end of each chapter, represents a measurement. In the many worlds view, every choice would create a new, physical copy of the entire book. In the many minds view, the book remains one and the same, but your experience of the story splits. You mentally follow the path to, say, the dragon's lair, while another, disconnected part of your awareness simultaneously follows the path to the enchanted forest. Both narratives are contained within the same physical object, but they are experienced by separate threads of your reading consciousness. The book hasn't multiplied, your mind has. This theory naturally raises a host of philosophical questions, the most pressing of which is the nature of personal identity. What does it mean to be you if your consciousness is constantly branching into non-communicating streams? If your mind splits every time you observe a quantum event, then with every glance, every thought, every decision, countless versions of your awareness are being spun off into experiential solitude. The you reading this sentence is just one thread in an unimaginably complex tapestry of your own potential minds. This challenges our deepest intuition of a unified self and suggests that individuality is far more fluid and fragmented than we ever imagined. The connection between all these mental branches is purely informational. They share a common origin and are described by the same quantum equations, but they cannot interact, share memories, or influence one another. The many minds interpretation, while elegant in its own way, is not without significant criticisms. One major objection is the issue of communication and shared reality. If the branching is purely mental, how do multiple observers ever agree on a single, consistent world? If you and a friend both look at the same electron, does your mind branch independently of your friend's mind? The theory must be carefully formulated to ensure that when two observers interact, their mental states become correlated, so that if your mind is on the branch seeing spin up, you will only ever meet and converse with versions of your friend whose minds are also on the branch seeing spin up. This preserves the illusion of a shared, objective world, even though its foundation is a network of interconnected, branching subjective experiences. Another criticism is that the theory seems to multiply the very thing it seeks to simplify. Instead of many worlds, we now have many minds, and it's not entirely clear if this is a more parsimonious explanation of reality. Yet, the enduring appeal of the many minds interpretation lies in the profound link it forges between consciousness and quantum mechanics. It takes the observer out of the passive role of a mere recorder and places them at the dynamic center of the quantum drama. In this view, the hidden connection we've been searching for is not a force or a field, but the very act of subjective experience. Our perception is the mechanism by which the fuzzy potentialities of the quantum world resolve into the sharp realities of our lived experience. It suggests that the cosmos and the conscious mind are not separate entities, but deeply intertwined aspects of a single, enigmatic whole, where the final frontier of exploration may not be outer space, but the infinite branching landscape within. As we navigate through the strange landscapes of quantum mechanics, we find ourselves searching for a framework, a new way of thinking that can make sense of this baffling non-locality. Our 25th theory offers precisely that, a radical and elegant vision of reality that seeks to explain these hidden connections not as bizarre exceptions, but as fundamental features of the cosmos. This is the implicate order proposed by the brilliant and unconventional physicist David Bohm. Dissatisfied with the standard interpretation of quantum theory, which he felt was incomplete, Bohm developed a model that portrays the universe as an unbroken whole, a flowing unity where separation is the real illusion. At the heart of his theory is a distinction between two coexisting realms of reality, the explicate and the implicate. The explicate order is the world we are all familiar with. It is the unfolded, tangible realm of everyday experience. The chair you're sitting on, the device you're watching this on, the planets and stars, all of these are part of the explicate order. Here, objects are separate, located in specific positions in space and time, and they follow the familiar rules of classical physics. It's the world of things, of boundaries and distinctions. This is the level of reality that our senses are built to perceive, and that our science has for centuries been so successful at describing. But Bohm argued that this explicit world is not the whole story. In fact, it's merely a surface manifestation, a temporary unfolding from a much deeper and more fundamental level of reality. This deeper level is the implicate order. The word implicate means enfolded. In this hidden dimension, the entire universe is woven together into an undivided totality. Nothing is truly separate. Everything is enfolded into everything else. Think of a simple, everyday example, a drop of ink. If you place a single drop of ink into a tall, viscous fluid like glycerin, and then slowly rotate the container, the ink will become stretched out into a long, thin thread until it seems to disappear completely from view. The ink has been enfolded into the glycerin. Its order is now implicate. Now, if you reverse the rotation, the thread will slowly coalesce, and the drop of ink will miraculously reappear, becoming explicated once more. In the implicate order, every location in space contains the entire universe in an enfolded state, just as every part of a holographic film contains the information for the whole image. The apparent separateness of objects in our explicate world is like the temporary, visible form of the ink drop. It's a fleeting manifestation from a deeper, unified background. The process that connects these two orders is what Bohm called the holomovement. This is not a movement of things through space, but a dynamic, unbroken process of folding and unfolding itself. The continuous flow of the universe from the implicate to the explicate and back again. In this ceaseless holomovement, the entire cosmos is actively and instantly interconnected. This provides a powerful philosophical and physical framework for understanding quantum non-locality, that spooky action at a distance. In Bohm's view, when two entangled particles influence each other instantaneously across a vast distance, they are not sending a signal faster than light through the explicate order. Instead, their connection is operating at the level of the implicate order, where their separation is ultimately an illusion. They are like two different ripples emerging from the same pond. Their seemingly independent motions are actually both expressions of the deeper, unified movement of the water itself. Their connection is immediate because in the implicate whole, they were never truly apart to begin with. To further clarify this mind-bending concept, consider the analogy of a flowing stream. On the surface, you can see various whirlpools, eddies, and droplets of water. These are the explicate phenomena. They appear as distinct, temporary objects with their own identities. You could focus on a single whirlpool, measure its size and speed, and study it as an independent entity. However, all of these seemingly separate forms are sustained by the continuous flow of the entire stream. They are not fundamentally independent things. They are perturbations, patterns within the unbroken movement of the water. If you could see the stream in its totality, you would understand that the whirlpool is not a separate thing, but a process within the whole. In the same way, Bohm suggests that every electron, every person, and every galaxy is a relatively stable, explicate feature that emerges from and is sustained by the hollow movement, the flowing, implicate totality of the universe. This perspective radically transforms our understanding of consciousness and our place in the cosmos. Bohm proposed that thought and matter are not separate substances, but are both derived from the same implicate order. The content of our thoughts, the flow of our consciousness, might itself be a manifestation of this deeper unfoldment. When we have an intuitive insight or a creative breakthrough, it could be understood as a moment where a new pattern unfolds from the implicate whole into our explicate awareness. This suggests that our minds are not isolated, skull-bound observers, but are participatory elements within the hollow movement. We are not looking at the universe from the outside. We are expressions of its unfolding, and our very act of observation is part of the cosmic process of bringing reality from its enfolded state into an explicate manifestation. In the vision of the implicate order, the universe is a single, undivided reality in a process of constant, dynamic flux, and we, in every thought and perception, are intimate participants in its endless dance of becoming. What if the force that binds us to our planet, the very pull of gravity itself, is not a standalone phenomenon, but is somehow intimately linked to the forces of electricity and magnetism? This leads us to a mysterious and highly controversial effect that has tantalized inventors and physicists for a century: the Biefeld-Brown effect. It all began in the 1920s when an inventive researcher named Thomas Townsend Brown made a peculiar discovery. He was experimenting with a special type of electrical capacitor, a device that stores an electric charge. But this wasn't just any capacitor. It was asymmetric, meaning its two electrodes were of different sizes. One electrode was a small, thin wire or a sharp point, and the other was a large, flat plate. When Brown applied a very high voltage direct current to this setup, something remarkable happened. The entire apparatus seemed to generate a faint but persistent thrust, a force that pushed it in the direction of its positive electrode. Brown, working with his mentor Paul Biefeld, believed they had stumbled upon something monumental: a direct link between electrostatics and gravitation, a way to potentially influence or even counteract gravity itself. The basic experimental setup is deceptively simple and can, in fact, be replicated by dedicated hobbyists today. Imagine a device often called a lifter. It consists of a lightweight, triangular frame made of balsa wood or wire. Along the base of the triangle runs a thin, positive wire electrode. Stretched above it, parallel to the base but separated by a small air gap, is a larger foil skirt acting as the negative electrode. When you connect this device to a source of extremely high voltage, often tens of thousands of volts with the positive lead on the wire and the negative on the foil, the lifter does something astonishing. It levitates, it lifts itself into the air silently and without any moving parts, seeming to defy gravity as it pulls itself toward the positive wire. This is the Biefeld-Brown effect in its most visually dramatic form, and it's this stunning demonstration that has fueled decades of speculation about its potential for revolutionary propulsion technology. However, the central and fiercely debated question is, what is the true source of this observed thrust? The mainstream scientific explanation, and the one most widely accepted, points to a purely classical phenomenon known as ionic wind. Here's how that works. The intense electric field around the small, positively charged wire electrode ionizes the air molecules around it, stripping electrons away and creating a cloud of positively charged ions. These positively charged ions are then violently repelled away from the positive wire and are strongly attracted toward the negatively charged foil skirt. As these ions accelerate through the air, they collide with neutral air molecules, transferring momentum and creating a net flow of air, a wind, in the direction from the positive electrode to the negative one. According to Newton's third law, for every action there is an equal and opposite reaction. The device pushing this stream of ions backward results in a forward thrust on the device itself. This is not a new or mysterious force. It's a well-understood electrohydrodynamic effect, and it explains why these lifters only work in an atmosphere. They are literally pushing against the air. Yet, proponents of a more exotic interpretation argue that the ionic wind explanation is insufficient. They point to experiments where a measurable thrust has been observed even in a partial vacuum, where there is very little air to serve as a propellant. If the effect were solely due to ionic wind, removing the air should cause the thrust to vanish completely. The persistence of any force in a vacuum suggests that there might be an additional, non-conventional component at work. This is the heart of the controversy. Thomas Townsend Brown himself was convinced that what he had discovered was an electrogravitic effect. He theorized that the high-voltage electric field was somehow directly interacting with the gravitational field, creating a genuine anti-gravity force. In this view, the asymmetric capacitor isn't just moving air, it's creating a push against space-time itself, with the positive charge acting as the leading edge of the thrust. This idea, if proven true, would be nothing short of revolutionary, offering a tangible link between electromagnetism and gravity, the two great forces that a unified theory of everything seeks to marry. The implications of a genuine Biefeld-Brown effect are profound, reaching far beyond simple levitation devices. For propulsion, it would open the door to entirely new classes of spacecraft engines. Imagine a thruster that requires no propellant at all. Instead of carrying vast tanks of fuel that are expelled to create thrust, a vehicle could generate motion by manipulating these alleged electrogravitic fields directly. Such an engine would be silent, would not produce a fiery exhaust, and could theoretically operate indefinitely as long as a power source was available. It would completely overturn the rocketry principle that has dominated space travel since its inception. On a more fundamental level, the effect hints at a deep and previously hidden connection in the laws of physics. Our current models treat gravity and electromagnetism as entirely separate phenomena. Gravity is described by Einstein's general relativity as the curvature of spacetime by mass and energy. Electromagnetism is a quantum field theory governing the interactions of charged particles. Unifying these two frameworks has been the holy grail of physics for a century. A demonstrable electrogravitic coupling, where a pure electric field can directly produce a gravitational-like force, would provide a critical experimental clue, a real-world phenomenon that any successful theory of quantum gravity would be forced to explain. It would suggest that the fabric of gravity and the dance of electric charges are two sides of the same cosmic coin. Despite the tantalizing possibilities, the Biefeld-Brown effect remains squarely on the fringes of established science. The burden of proof lies with those claiming it is more than ionic wind. To be widely accepted, the effect would need to be rigorously demonstrated in a hard, high-quality vacuum, with all possible sources of experimental error accounted for, such as the influence of the high-voltage corona on the surrounding chamber or electrical forces on the support wires. Reproducible, peer-reviewed data from such an experiment is still lacking. The effect lies in a shadowy realm, too persistent to be completely dismissed as fraud, yet not conclusively proven to be the world-altering phenomenon its champions believe it to be. It stands as a powerful reminder that our understanding of the universe is not yet complete, and that hidden connections may still lurk in the most unexpected places, waiting for a precise experiment or a brilliant theoretical insight to pull them into the light and change our vision of reality forever. But if our minds are truly branching and fragmenting at the quantum level, where does this incredible processing power actually reside? What is the physical machinery that could possibly support such a profound connection between the ethereal world of consciousness and the concrete laws of physics? This brings us to a theory that places the seat of our awareness deep within the architecture of our own brain cells. Welcome to the Orchestrated Objective Reduction Theory, or ORCH, a bold and controversial proposal from anesthesiologist Stuart Hameroff and Nobel laureate physicist Sir Roger Penrose. This theory makes a staggering claim. Consciousness is not simply the result of ordinary neural firings, but arises from quantum computations happening within tiny structures called microtubules inside the neurons of our brain. To understand this, we first need to look at what microtubules are and what they do. Imagine the bustling interior of a single brain cell or neuron. It's not just a simple blob, it's a highly organized city with a complex cytoskeleton that gives it structure and acts as its transportation network. Microtubules are the tiny protein tubes that form a major part of this cellular scaffolding. They are incredibly small, with diameters measured in nanometers, but they are essential. They help maintain the cell's shape, they act as railways for transporting molecules, and they play a key role in cell division. In neurons, they are particularly abundant, forming a dense, intricate network. For Hameroff, this intricate network looked less like simple scaffolding and more like the ultimate microchip, a perfect candidate for hosting the unimaginably complex computations that could give rise to conscious experience. The real magic, however, comes from Penrose's contribution, which deals with the deepest mystery of quantum mechanics, the collapse of the wave function. As we've seen, a quantum system can exist in multiple states at once, a superposition until it is measured, at which point it collapses into one definite reality. But what exactly causes this collapse? The standard Copenhagen interpretation says it's the interaction with a classical measuring device, but this has always felt unsatisfactory, leading to endless paradoxes. Penrose proposed a radically different answer. He suggested that wave function collapse is not triggered by consciousness, but by gravity. His idea, known as objective reduction, is that a quantum superposition becomes unstable all on its own. The tiny separation in space-time geometry created by an object being in two places at once eventually becomes too much for the universe to handle, and the superposition spontaneously collapses into a single state. The key point is that this collapse is not random. Penrose believed it is a moment when the universe accesses non-computable information, a flash of insight that transcends mere algorithmic processing. The ORCH theory brilliantly weaves these two ideas together. It proposes that within the microtubules of your neurons, electrons can become isolated in a quantum-friendly environment, allowing them to enter a state of superposition and quantum entanglement. These quantum states can persist long enough to perform complex computations, a process known as quantum coherence. According to the theory, these coherent states are orchestrated by the brain's biological processes, which organize and fine-tune the quantum vibrations. Then, in accordance with Penrose's objective reduction, these large-scale superpositions eventually collapse. It is in this moment of orchestrated, objective collapse that a flicker of conscious experience occurs. Each collapse is a discrete event, a quantum bit or qubit of consciousness. Your stream of awareness in this view is not a continuous flow, but a series of these tiny, rhythmic collapses happening perhaps 40 times a second, weaving together to create the rich tapestry of your inner world. This theory provides a stunning potential bridge between the brain and the cosmos. If consciousness arises from quantum processes in microtubules, and if those processes are ultimately governed by the fundamental geometry of spacetime as Penrose suggests, then our minds are not just trapped inside our skulls. They are intimately connected to the fabric of the universe itself. The same quantum gravity that shapes the destiny of stars and galaxies may also be orchestrating the very thoughts in your head. This idea takes the connection to a truly cosmic scale. Some speculations within this framework even suggest that the quantum information in these microtubules isn't destroyed when the body dies. Instead, it could perhaps dissipate back into the universe, a drop of conscious experience returning to the cosmic ocean from which it came. This is, of course, highly speculative, but it illustrates the profound linkage the theory proposes connecting the architecture of a single protein inside a single brain cell to the fundamental laws governing the entire cosmos. Naturally, a theory this revolutionary has faced immense scrutiny and criticism from the mainstream scientific community. The primary objection is the issue of the warm, wet, and noisy environment of the brain. Quantum coherence is an incredibly fragile state. In laboratories, physicists go to extraordinary lengths to achieve it, using temperatures near absolute zero and isolating systems from all external vibrations. The brain, by contrast, is a warm, bustling, and chaotic place, seemingly the worst possible environment for maintaining delicate quantum superpositions. Critics argue that any quantum coherence in microtubules would be destroyed almost instantly, far too quickly to have any meaningful role in neural processing. Proponents of ORCH counter this by pointing to new evidence of quantum effects in biological systems, such as the quantum coherence observed in photosynthesis, where plants use quantum tricks to transfer energy with near-perfect efficiency at room temperature. They argue that the unique structure of microtubules with their ordered lattices of tubulin proteins could be evolutionarily designed to protect quantum states, acting as quantum capacitors or waveguides. The debate is far from settled, but the power of the ORCH theory lies in its audacious scope. It doesn't just try to explain consciousness, it attempts to place it squarely within the framework of fundamental physics. It suggests that the emergence of mind was not an accident of biology, but may be a fundamental feature of a universe whose laws naturally give rise to awareness. In this vision, the hidden connection is not just between entangled particles, but between the quantum geometry of reality and the qualitative feel of our own existence. Your sense of self, your deepest thoughts, and your moments of creative inspiration may be the result of the universe constantly resolving its own quantum uncertainties, with your brain acting as the most sophisticated instrument for orchestrating this cosmic process. We've plunged into the crushing density of black holes and the paradox of lost information, but what if there's a cosmic counterpart, a yin to that dark yang? This brings us to the white hole hypothesis, a concept that sounds like pure science fiction, but emerges straight from the mathematics of general relativity. If a black hole is a region of spacetime from which nothing, not even light, can escape, then a white hole is its exact theoretical time reversal, a region of spacetime that cannot be entered from the outside, but from which matter and light can only ever emerge. Imagine a black hole in reverse. Instead of a cosmic drain pulling everything in, it's a cosmic fountain, perpetually spewing out energy and matter, yet utterly impenetrable. No spaceship could ever fly into it. Any approach would be met with an irresistible repulsive force, a kind of cosmic keep-out sign written into the fabric of reality itself. While we have overwhelming observational evidence for black holes, a white hole has never been conclusively detected. So why do physicists take the idea seriously? Because the equations of Einstein's general relativity are, in a profound sense, time-symmetric. They work just as well running forwards as they do backwards. The same math that describes the relentless gravitational collapse of a star into a black hole also permits a solution for an object that is eternally exploding outward. The challenge is that while black holes are a natural, almost inevitable endpoint for massive stars, there's no known physical process that would actually create a white hole in our universe. It would have to be a primordial object, a feature baked into the cosmos from its very first moment. This, incredibly, leads to one of the most breathtaking possibilities in all of cosmology, that the single biggest white hole we know of might be the Big Bang itself. Think about the defining characteristics of the Big Bang. It marks a boundary, a beginning to our space-time where all known laws of physics break down. From that singular point, the entire universe, all matter, energy, space, and time exploded outward. It is, by definition, a region we cannot look beyond or travel back into. It is the ultimate one-way exit. In this view, our entire cosmic history is the ongoing eruption from a white hole event. This reframes the creation of the universe not as an inexplicable singularity in nothingness, but as the natural output of a pre-existing, though entirely separate physical structure. The Big Bang becomes less of a bang and more of a cosmic discharge, the visible output of a process occurring in a realm beyond our own. This idea weaves an even deeper connection when we consider the life cycle of black holes. If a black hole is the ultimate endpoint of gravitational collapse, and a white hole is its reverse, could they be two sides of the same coin? Some theoretical models suggest that what we perceive as the interior of a black hole might, through a complex bridge in space-time known as an Einstein-Rosen bridge or a wormhole, connect to the interior of a white hole in another universe. In this stunning picture, when matter falls into a black hole in our cosmos, it isn't crushed into oblivion at a singularity. Instead, it is funneled through this cosmic tunnel and erupts out of a white hole, becoming the seed for an entirely new universe. In this cosmic recycling model, every black hole in our universe could be a birthing chamber for a separate cosmos, with its own laws of physics potentially emerging from the specific way the matter entered. The implications of this are dizzying. It suggests that our universe may not be a solitary creation, but one branch in an infinite fractal tree of universes, each born from the collapse of a star in apparent reality. Your existence here and now could be indirectly linked to the gravitational death of a massive sun in a cosmos that existed long before our own. This provides a potential, deeply elegant solution to the puzzle of what happens to the information that falls into a black hole. Instead of being lost in a paradox, the information is simply transferred, encoded into the initial conditions of a newborn universe. The black hole information paradox is resolved not within our universe, but by acknowledging a larger, multi-universe reality where information is always preserved, just not always in the same place. Of course, the white hole hypothesis remains highly speculative, facing significant theoretical hurdles. For one, the wormholes connecting black holes to white holes are typically unstable, collapsing instantly unless propped open by some exotic form of matter with negative energy density. Furthermore, the violent conditions inside a realistic black hole with tidal forces and quantum effects might prevent any such bridge from forming. Yet, the idea persists because of its profound explanatory power and its beautiful symmetry. It links the largest and smallest scales of existence, connecting the destiny of a single particle falling into a black hole to the origin of an entire cosmos. It transforms the universe from a one-off event into a potentially endless cycle of birth, transformation, and rebirth, where every ending is secretly a new beginning in a reality we can never see, but whose existence would mean we are all part of something infinitely grander than we ever imagined. We've been hunting for dark matter for decades, trying to identify the mysterious substance that makes up about 85% of the universe's mass. We see its gravitational influence everywhere, in the way galaxies spin far too quickly to hold themselves together, in the way light bends around massive clusters, in the very large-scale structure of the cosmic web. Yet, for all our searching, we haven't found the particle responsible. But what if we've been looking in the wrong place entirely? What if dark matter isn't a sea of exotic, undiscovered particles, but a universe teeming with ancient, invisible cosmic fossils? This leads us to a theory that connects the first instance of creation to the dark heart of every galaxy, the idea that dark matter is composed of primordial black holes. Primordial black holes are fundamentally different from the ones we're familiar with. The black holes we know and study form from the dramatic collapse of massive stars at the end of their lives. A star many times heavier than our Sun burns through its fuel, can no longer support its own weight and implodes, creating a black hole. Primordial black holes, however, wouldn't need a star. They are thought to have been forged in the extreme conditions of the very early universe, less than a second after the Big Bang. At that time, the cosmos was not smooth and uniform. It was a seething, chaotic soup of energy, roiling with intense density fluctuations. In some regions, the density could have been so high that gravity overwhelmed the incredible outward pressure of the expanding universe, causing pockets of space to directly collapse. There was no star, no supernova, just pure, raw density crushing itself into a black hole. Their masses wouldn't be tied to stellar physics, but to the specific conditions of those first moments. They could range from the mass of a small asteroid to many times the mass of our Sun, all depending on the size of the primordial density peak that spawned them. This idea creates a breathtaking hidden connection between the largest and smallest scales of existence. The same quantum fluctuations we discussed earlier, the microscopic jitters that were amplified by cosmic inflation to become the seeds for galaxies, might also have had a more dramatic effect. The most intense of these fluctuations wouldn't just create slightly denser regions of gas, they would collapse all the way into black holes. In this picture, the invisible dark matter that provides the gravitational scaffolding for galaxies to form isn't a cloud of weakly interacting particles. It is instead a swarm of these primordial black holes, scattered throughout the universe in vast numbers, their collective gravity shaping the cosmos from the very beginning. They would be the universe's hidden architecture, the dark framework upon which the luminous world of stars and galaxies was later built. This theory has gained renewed interest in recent years, especially after the groundbreaking detection of gravitational waves by the LIGO Observatory. When LIGO detected its first black hole merger, it revealed something surprising. The black holes involved were significantly more massive than most stellar mass black holes we had observed before. While stellar processes can explain some of this, it opened the door to the possibility that LIGO was seeing mergers of primordial black holes that had been drifting through dark matter halos for billions of years. If vast numbers of these ancient black holes exist, some of them would inevitably find each other, form binary pairs, and eventually spiral together in a cataclysmic merger, rippling the fabric of spacetime. These gravitational wave signals could be our first direct evidence of the dark matter that has eluded us for so long. Of course, this elegant idea faces significant challenges and constraints. If the universe were filled with enough asteroid-mass primordial black holes to account for all dark matter, we would expect to see their influence through a phenomenon called gravitational microlensing. As one of these small, dark objects passed in front of a distant star, its gravity would briefly bend and magnify the star's light, causing a telltale flash. Extensive surveys, however, have not found nearly enough of these microlensing events to support the idea that all dark matter is made of small primordial black holes. This has largely ruled out a universe dominated by these lighter objects. The window for this theory now seems to lie with black holes of larger masses, in a range that is harder to constrain with current microlensing searches. The possibility remains that a significant fraction, perhaps not all, but a crucial part of the dark matter budget is composed of these more massive primordial relics. The profound beauty of this theory lies in its power to solve two of cosmology's greatest puzzles with a single, deeply interconnected concept: the mystery of dark matter's identity and the mystery of the universe's initial conditions could share a common solution. The same quantum birth pangs that gave us galaxies also gave us the invisible anchors that hold them together. It suggests that the dark side of the cosmos is not a separate, alien realm, but is built from the same primordial stuff as the stars we see, simply taking a different, more extreme path in the first fleeting moments of time. The search for these ancient black holes continues, a hunt for the universe's oldest and most secretive inhabitants, whose discovery would forever link the fiery dawn of creation to the dark, silent embrace that binds the galaxies. But what if the very ticking of the cosmic clock, the steady forward march of time we take for granted, is itself an emergent property of a deeper, more rhythmic reality? This brings us to our final and perhaps most rhythmically profound theory, the possibility that our universe is a time crystal. The concept of a time crystal sounds like a contradiction in terms. We're familiar with spatial crystals like diamonds or snowflakes. Their atoms are arranged in a repeating, periodic pattern in space. A time crystal takes this idea and projects it into the fourth dimension. It is a physical system that exhibits a repeating, periodic pattern not in space but in time. Its ground state, its most stable and lowest energy configuration, is not static. It is a state of perpetual, cyclical motion, a structure that oscillates forever without any energy input, breaking what physicists call time translation symmetry. To grasp this strange idea, imagine a perfectly frictionless clock that, once wound, ticks back and forth forever without ever needing to be rewound. Now imagine that this perpetual ticking isn't driven by stored energy, but is the clock's default, most natural state of being. This is the essence of a time crystal. Its components, be they atoms, ions, or something else, don't just sit still. They flip between two or more configurations in a fixed, unwavering rhythm, a rhythm that is robust and persists even when the system is isolated from the environment. This isn't a violation of the laws of thermodynamics. The crystal isn't creating energy. It's in its ground state, but that state is dynamically ordered, a dance frozen not in space but in time itself. Since their theoretical proposal, small-scale time crystals have been successfully created in laboratories using complex systems like chains of trapped ions or dense ensembles of spinning atoms, proving that this bizarre form of matter is not just a mathematical curiosity, but a real physical phenomenon. Now, let's take this mesmerizing concept and inflate it to a literally cosmic scale. Could the universe itself be a four-dimensional time crystal? Imagine the entire cosmos, from the quantum foam at the Planck scale to the vast supercluster filaments, as a single, unified structure whose most fundamental state is not a static void but a continuous cyclical oscillation. In this view, the regularities we observe, the steady beat of atomic clocks, the predictable orbits of planets, the relentless expansion of space, are not separate phenomena. They are all manifestations of this underlying cosmic rhythm. The universe isn't just in time, the universe itself is time, structured and crystalline. The fundamental constants of nature, those seemingly fixed numbers like the fine structure constant, might not be arbitrary. They could be the emergent properties of this grand cosmic crystal's specific vibrational mode, much like the resonant frequency of a guitar string is determined by its tension and length. This perspective forges a hidden connection of immense scope, linking the quantum world directly to cosmic evolution. The universe's expansion, rather than being a one-way street from a hot Big Bang to a cold, dark end, could be part of a much longer, rhythmic cycle. Perhaps the cosmos breathes, with each tick of the time crystal corresponding to an expansion phase and each tock to a contraction, not in a classical cyclical model, but in a more fundamental four-dimensional pattern. The arrow of time, the mystery of why we remember the past and not the future, might find a new explanation here. In a time crystal universe, the forward direction of time could be an emergent property of the crystal's broken symmetry, the same way a magnet has a specific north-south orientation, even though the underlying laws are symmetric. Our perception of time's flow would be a local experience of this global crystalline structure. The implications resonate with many of the theories we've already explored. The holographic principle suggested that our three-dimensional reality is a projection from a two-dimensional surface. A time crystal universe adds a temporal dimension to this idea. The entire four-dimensional block of space-time could be the emergent holographic projection of a deeper, timeless, and crystalline reality. The strange, non-local connections of quantum entanglement could be understood as the natural correlations between different parts of this cosmic crystal, instantaneous because they are all part of a single, unified, oscillating whole. Even our own consciousness, with its rhythmic brainwaves and perception of a flowing present, might be a localized, biological reflection of the universe's own fundamental, ticking nature. In this grand and poetic vision, we are not just living in a universe that has time. We are living inside a universe that is time, a single, magnificent, four-dimensional time crystal, perpetually oscillating in a dance of existence whose rhythm defines every law of physics and every moment of our lives. And so, we have journeyed through 30 astonishing windows into the hidden architecture of reality. From the holographic projection of our three-dimensional world to the spooky embrace of quantum entanglement, from the cosmic butterfly effect that links quantum jitters to galaxy clusters to the life-friendly fine-tuning of the Anthropic Principle, a single recurring theme has emerged with stunning clarity. Our universe is not a collection of isolated fragments drifting in a meaningless void. It is a profoundly interconnected, deeply relational whole. The dance of the smallest particles is inextricably linked to the fate of the largest cosmic structures, and our own consciousness may be the universe's way of awakening to its own magnificent and intricate design. Whether we are contemplating the cyclical collisions of brains in the ekpyrotic universe or the static, eternal existence of the block universe, these theories all point toward a reality where separation is the ultimate illusion. The gravitational tug of dark flow hints at realms beyond our cosmic horizon, while Mach's principle suggests the inertia of a single atom is shaped by the collective mass of all existence. The panpsychist view imbues the cosmos with an inner light, and the simulation hypothesis reframes it as a grand computation. Each idea, whether grounded in rigorous mathematics or soaring on the wings of speculation, serves to stretch the canvas of our understanding, revealing a cosmos far stranger, more wondrous, and more unified than we ever dared to imagine. This grand tapestry of interconnection challenges our most fundamental assumptions about who we are and where we belong. We are not merely passive observers on a tiny rock in a vast, indifferent cosmos. The revelations of these theories suggest we are active participants in a living, breathing, and perhaps even conscious universe. Our act of observation may crystallize reality from quantum potential. Our thoughts may be quantum computations orchestrated by the fabric of spacetime itself, and our very sense of self might be a localized expression of a cosmic mind. This perspective is simultaneously humbling and empowering. It diminishes our ego, revealing that we are but a fleeting whisper in the cosmic story, while simultaneously elevating our significance, casting us as the senses through which the universe can know itself. As we stand at this frontier of understanding, it is crucial to remember that the journey is far from over. Each of these theories, from the well-established to the highly speculative, represents a stepping stone. They are not final answers, but invitations, provocations to think bigger, to question deeper, and to remain forever curious about the hidden threads that weave the fabric of everything. The greatest discoveries often lie not in the answers we possess, but in the beautiful, bewildering questions that remain. The search for a unified theory of everything, for the true nature of consciousness, and for our ultimate place in the grand scheme continues, and it is the most thrilling adventure humanity has ever undertaken. This expansive view of a connected cosmos is more than just an intellectual exercise. It carries a profound resonance for how we live our lives, recognizing that we are fundamentally linked to each other, to this planet, and to the distant stars can inspire a deeper sense of responsibility, wonder, and kinship. It invites a shift from a mindset of separation to one of integration, encouraging us to see the universe not as something out there, but as our extended home, a community of existence of which we are an inseparable part. The sense of cosmic loneliness that once defined our species can be replaced by a feeling of belonging to an immense, dynamic, and breathtakingly beautiful whole. Now the adventure turns to you. We have explored these 30 theories together, but the conversation is just beginning. We want to hear which of these ideas resonated most deeply with you, which one stretched your mind or challenged your perception of reality. Was it the holographic principle that captivated you, or the haunting mystery of the black hole information paradox? Did the eternalism of the block universe change how you think about time, or does the Gaian vision of a living cosmos speak to you? Share your favorite theory and your own thoughts in the comments below. Let's continue this incredible discussion as a community of cosmic explorers. If this journey into the universe's hidden connections has ignited your curiosity, there is so much more to discover. To ensure you don't miss our next exploration into the mysteries of space, time, and existence, make sure to subscribe to the channel and hit the notification bell. We are just getting started, and the cosmos holds endless wonders waiting to be uncovered. Thank you for embarking on this extraordinary intellectual voyage. Keep looking up, keep questioning, and never lose your sense of wonder. The universe is a vast, interconnected, and deeply mysterious place, and our greatest privilege is to be here right now with the capacity to try and